Testing audio, 1, 2. Anyone can hear me, maybe give me a confirmation by commenting. That would be great. Okay, perfect, thank you. We're gonna go ahead and get started here in probably about a minute or two, just to make sure we have some people joining. We're getting a good amount of people joining. That's fantastic. We'll start again just here, just a quick moment. All right, I'm showing 6 o'clock, but I usually want to kind of give it about another minute just in case anyone else wants to join in. All right. I can minimize that. All right, looks like we got a good amount of people here. That's fantastic. Going to go ahead and get started. I got, should be 6:01 right now. Thank you so much for joining. This is our second advanced storm spotter class that we will be doing for this season of storm spotter talks that we've been doing now for several weeks. Like I said, thanks for joining. My name is Kevin Gilmore with the National Weather Service New Orleans Baton Rouge office located in Slidell, Louisiana. A lot of you probably have seen me before do Facebook Lives. Usually I'm no stranger to doing those. May have seen me around, but I'm one of many people here, great meteorologists at the Warning Forecast Office here at the National Weather Service and Slidell, who do a great job at forecasting and getting timely warnings out to you and forecast. And like I said, I'm one of many on this team that we have here doing these spotter talks. If you took the broadcast or the basic course earlier this week, that was my meteorologist, Mike Efferson. We got a lot of great forecasters here, and I'm going to be doing the advanced storm spotter class here for tonight. So again, thanks so much for joining, and we're going to really dive into it. And I will kind of give you a heads up now. This is advanced. This is going to be covering a lot of very in-depth topics, and they may come at you pretty quick, and I'll try and slow down as much as I can. Try and make sure as thorough as make as thorough understanding as possible. What we're going to try and do for this one, when I did the basic course, when I started this out in March, I kind of encouraged questions all throughout it because I want to make sure everyone has a very good solid understanding of it, but mostly just due to the time-wise, the fact that this could go long, we're going to try and keep all questions in the middle part. There's going to be a break in the middle, and I'll kind of address those. However, if you can comment at any time. I'm not going to unmute anyone during this, but please, if you have any questions, you can, if you want to, you can go ahead and just send them in the questions portion of the GoToWebinar, and I'll see them by the middle portion of the talk when we take that break, and we'll address the questions then. So with that said, we'll go ahead and move on and go ahead and talk about what we will be talking about here. And also, I just want to make sure, see, actually, I can kind of clarify that myself, so that my screen's being shown and you can hear me. So I'll check back from time to time the questions. If something weird happens, you can't hear me or you can't see my screen, or there's a technical error, I'll be checking. Just drop a lot of comments in the question bar there, and I'll be able to check them too. But otherwise, like I said, I'll go ahead and go forward with this, so with the talk. So topics to cover, there's going to be lots of them here. We're going to do a quick introduction about who we are, and we're going to kind of like just take a quick basic course review, kind of not really get in depth to talk about much about what we did with the basic course, but we're going to jump straight right into the good stuff. We're going to go right into the severe weather forecasting, synoptic meteorology, severe weather ingredients, computer models, the things that we look at to produce the forecast to determine if there's a risk for severe weather. We want you to be also very much aware to understand what we're looking at as well. And then radar meteorology 1 and 2 split up sections. This is going to be radar meteorology 1, which is going to be the basics, base products, common signatures, and then talk about radar meteorology 2, which is dual pole. And if that's something new, that's a new term you haven't heard before, we'll go over all about that. Supercell structure, storm mode and motion, and associated threats. Tornadoes, waterspouts, types, and myths, things that you need to know about that. Available products that you can use yourself, and kind of a refresher on the storm reporting procedure, and then we'll take questions at the end. So moving ahead here. Now, this is a slide that I showed my basic course, just in case there's someone who did not take it. I wanted to kind of remind everyone that, of course, the National Weather Service New Orleans Baton Rouge office is a 24/7 operations. We always have a forecaster on staff. We are one of 122 offices across the contiguous United States, and we cover 22 parishes of southeastern Louisiana and 8 Mississippi counties in southern and southwestern Mississippi. We do have a upper air station on site, as well as a WSR 88D radar that you see in the top right there in the photo. We cover around 2.9 million people in our CWA as well. So our neighboring offices include National Weather Service Lake Charles to our west, National Weather Service Jackson, Mississippi to our north, and National Weather Service Mobile to our east. So we're surrounded by 3 offices, and we're constantly coordinating, especially people wonder a lot of times what happens when a tornado forms in one area and moves into the other. Well, we coordinated. And if we have a tornado warning for Wilkinson County and it's moving into some other county in southern Mississippi adjacent, then we'll have to issue a warning for that. We'll issue a warning for that, but we'll have to actually coordinate with Jackson to make sure that they continue the polygon into their area. So very interesting the way that we coordinate. We make sure that communication is key. It's a very important part is communication. But if you happen to have family and friends, or you're watching from any of these surrounding offices, be sure to follow them on their local Facebook and Twitter, as well as going to their website. Now, the purpose of advanced spotter training, we want to actually apply transparency to how meteorologists in the National Weather Service work behind the scenes. This is going to be based out of either forecasting or even during meteorology and during the analysis portion, which is going to be taking a look at radar signatures. And we want you to have an elevated skill set that can bring confidence to your storm chasing and storm spotting and storm reporting procedure. And to do that, we want you to have a solid understanding of storm structure. We want you to have a little bit more confidence now that you know what you're seeing, and that connect. And a term creates a better connection in our spotter network, which is extremely important there, especially the communication. And as we always say, we still need your reports. That this is a very important course. And again, I'm glad that we have such a great audience here. And we're going to talk about the proper ways, of course, as a reminder, more from the basic course here towards the end of the presentation. And of course, if you're interested in the Storm Spotter Field Guide, we don't print these. Now, of course, pre-COVID, where we would be doing these spotter classes in person, we don't actually print these anymore. So we don't even hand these out like we used to in the past. So they don't hand us out. They're not even shipped to our WFO at all. So if you're interested, you can print these out with the web link below. They're 36 pages double-sided. I personally like to have one on me. I guess you could call me old school. I like to always have paper in my hand, sometimes referencing some things. So if you're interested, print it out, make a really cool binder out of it, but it is available. Now, severe weather forecasting, we're going to dive straight into the good stuff here. And we're going to cover a lot of different subtopics. That's going to include synoptic meteorology, getting into the effects of parcels. And I have to remind you, again, some of this gets a little bit complicated. I'm going to do a real basic overview of this and try to explain it the best I can, where to expect severe weather, even meteorological parameters. I'm sure if you've watched TV meteorologists on broadcast Mets on TV, they'll talk about these weird different values like CAPE and shear, bulk shear, and things, or things that just seem kind of confusing to you. But we're going to go over all of those, or at least some of the more basic ones. and even numerical models too, and even some helpful tools to help even you to track these parameters to do some severe weather forecasting of your own. So synoptic meteorology, a quick overview, is just basically known as the large scale picture. When we say synoptic, that's just large scale. That's if you talk about a range, you want to kind of apply a numerical value to it, that's around 620 miles to around 1,500 miles. So we're talking about big scale systems, high pressures, low pressure systems, frontal boundaries, troughs and ridges in the mid levels. Those are synoptic scale features. They're not small scale. Small scale is going to be individual thunderstorms and things like that. So that's what we mean by synoptic meteorology. That's all these big players in the atmosphere, these big high pressures and low pressures that move around and strengthen or weaken with time, and kind of have show a balance between each other over time. And of course, all this occurs in what we call the troposphere. And the troposphere is a very small part of the atmosphere, and a lot of people don't realize that that the weather really only occurs in the lowest 3 to 4% of the atmosphere. So as you see with the charts here, right there, that's just the troposphere. You have above that the stratosphere, the mesosphere, and the thermosphere, and then eventually you're just pretty much in space by that point. Now, in between those different layers, we have it denoted by like a tropopause, stratopause, and mesopause. So I'm going to use this term a lot. I'm not going to talk about the stratosphere. I want to just show you that there's more of the atmosphere than actually that we're going to be talking about here. But mostly we're going to be talking about just that lowest part of the troposphere. It only extends around 4 to 12 miles high. For the rest of it, that extends around over 320 miles high. So that's just the weather there. We're going to be talking about that troposphere and then the layer between the troposphere and stratosphere, which is called the tropopause. That's where we talk about temperatures cooling with height, because as the sun beats down on the surface, it really warms the surface up a lot. As you get away from that long wave radiation, that re-emission of the radiation from the solar, from impacts of the sun reaching the surface and bouncing back out, it gets cooler as you get further aloft. But then you get to the stratosphere, it actually warms again. And that's actually where we call the ozone and the ozone layers within that region. It actually warms there, and that's where gases get trapped. Really, like I say, weather rarely gets into the stratosphere. It could pierce through the tropopause sometimes with what are called overshooting tops, or the part of the updraft that really pierces through strongest enough to get into the stratosphere. But again, don't worry about that right now. We're going to talk a little bit more about it, but just wanted to show you that we're going to be talking a lot about the troposphere here. And of course, here's basically, I just jumped ahead here explaining that how the sun heats the surface near surface atmosphere due to, I had that wrong, shortwave radiation, and it remains warmer. So we're talking about a cooling aloft. The atmosphere almost always cools at a certain rate aloft. Now, Coach, you'll notice that temperatures become consistent. It's begin to warm slightly into the stratosphere, like I was just talking about. Now, that's why storms have to basically hit a top part. They can't go any higher. You're talking about cirrus clouds and upper level clouds, anvils. Eventually, clouds can only go so far up. And that's because they hit that warming inversion. They hit the tropopause, which really averages around maybe 25 to 35,000 feet, but can actually lower a lot lower than that when the atmosphere is a lot colder. It's been as low as maybe 10 to 15,000 feet when it's extremely cold, like maybe up in the pole regions of the Earth. But clouds don't go any higher than that. We almost never get clouds into the stratosphere. And like I said, that's where we're going to be focusing the most there. It's just the troposphere. Now, just talking about the troposphere, now we're going to just focus in on that. Now, as we know, as elevation increases, the number of molecules decrease and the density of the air also does as well. Therefore, there's a decrease in air pressure. So the way I like to think of this is, and this is what this next example explains, is that think of it as you're diving in a swimming pool. As you dive to the bottom of the swimming pool, you get a lot of pressure on your ears. And that's due to the weight of the water above you. There's a lot of water on it. So that's pressure, it's pushing down. So the pressure at the surface is always going to be a lot higher than as you get further up aloft, because you have less air pressure or less air on top of you as you get higher. So we measure that air pressure using millibars. So a typical pressure, what we call the average sea level pressure for Earth down on the surface, is 1,012.25 millibars, I believe, around that region. So around 1,000 millibars. So as you get higher up, what we call the mid levels of the atmosphere, that's around 500 millibars. So that's generally around 18,000 feet, as you see there. And then you get further up, you get 300 millibars, then 200 millibars. So you're having less of the atmosphere above you. So there's definitely less left air parcels, and it's definitely less dense up in that area. And that's where airplanes travel. You're talking about 300, 250 millibars and 200 millibars around that region. There's not much air there, and it's extremely cold. That's why if you're flying in an airplane, you have to have a vacuum in your cabin because there's less air pressure outside that, and it's extremely cold. You can't be exposed to conditions like that as you get that far up in the atmosphere, because temperatures up in that region can sometimes be as high as, as cold as -30, -40, -50 Celsius, which is absolutely just really cold. So that's what we're talking about. We're talking about these layers. So we as meteorologists use these layers to talk about different effects. Like we want to call it like layers of a cake in a way. Let's see if I can actually show the next animation here. It's actually, there we go, jumping ahead, slowing down there we go. So that's what we're talking about. There's different layers of the atmosphere, like layers in a cake. We like to typically identify moisture and wind patterns at the surface to the lower tropospheric levels, which is around 850 and 700 millibars. Then we get what are called ridges and troughs at 500 millibars, or the middle part of the troposphere. That's usually types of systems that help form surface features like high pressure systems and low pressure systems. And then above that, what drives even that are jet streams. So the jet stream can vary between 200 and 300 millibars, usually depending on the time of the year and your latitude in response to the location on Earth. So that's where we're talking about the jet stream, and then we got ridges and troughs, and then we're identifying moisture and wind at the low levels. Now, of course, you can identify moisture and wind at any level, but that's primarily the focus for those levels of what we're looking at. Of course, temperature too. If you've ever heard of temperature advection, which is the change in temperature with location, that's also a good feature as well. So there's a lot of different layers that we're looking at here. As forecasters, we're looking at the intensity of the jet stream, the amplification of ridges and troughs, the amount of moisture and wind changes over time, and all this means completely different weather that's occurring at the surface. So it's a delicate balance, and as I honestly have always said to myself, forecasting, almost all storm systems are completely different. Some have some similarity characteristics, but I've never seen two systems produce the exact same weather. It just doesn't happen. There's going to be something aloft or at the surface that's just a little bit different, and there's just a slight difference in it. It can mean a complete different scenario. So we're going to be talking about a lot with this. So now I want you to think about that 500 millibar layer that I just showed you before. Now, it's important to remember that constant pressure is not the same as constant altitude. So I'm showing you back here, you're thinking to yourself, okay, well, 500 millibars is typically 18,000 feet. Well, if it's a really cold atmosphere and there's a lot more dense cold air in the vertical column, that's going to be a lot more compression. So those colder temperatures, those millibars, there's going to be higher pressure, which makes sense for high pressure at the surface when it's cold. As you see behind the front, you got a high pressure coming behind the front. So that's a lot of sinking and compressing air going on there. So what happens is all the pressure level increases as you go down. So it gets compressed. So what happens is the actual 500 millibar height gets pushed down in altitude. And then the warm air is the opposite effect. It actually rises. So that means in troughs, as we call it, think of it as like a trough, like a bowl in the atmosphere. So at 500 millibars, when we see a trough, a bowl, that's a lot of cold air, which is compressing the heights down. So it looks like a bowl in a way. A ridge is the exact opposite. And it looks basically like this. This kind of gives you a little bit more 3D schematic, what I'm talking about. You get that constant pressure surface, and you get the cooler, more dense air presses that pressure down, and the warmer, less dense air rises it. And the effect of that is a map like this. This is what we call a constant height chart. And what you're looking at is 500 millibars and what we call height anomalies. Basically, don't worry about that. I want to kind of really give a perspective of what we mean by troughs and ridges. You see that there's different values there. You see all those different numbers on those lines going across. It almost looks like a contour map. Different levels, because those are different pressures for 500 millibars. So it varies differently with heights. So you see that blue area there in the middle is a trough, or it's like a bowl that's affecting there. So there's definitely a lot of sinking going on, which means that the 500 millibar heights have dipped down. So there's a trough there, and then you have a ridge over the eastern United States where the heights are really high. So similar to what I just showed before, with the warm, less dense air rising and the cooler air sinking, you get these differences here. So again, this is at 500 millibars, showing you the different heights of the 500 millibar level. So because of that, we can see really cool things like how low pressure systems can form near these dips and these rises, how high pressure systems form as well, which translates like this to the surface. We get a low pressure system near these troughs. We get high pressure near these ridges. And it's this delicate balance between the two. When ridges are stronger, some could be weaker. Storm systems can be stronger. Low pressure systems can be stronger. There's a whole amazing balance between the two that can actually form this really delicate balance between these two. So that's what we basically mean by that. And of course, again, I'm just going over a lot of this. I didn't want to go into what height anomalies are, which essentially is just is the 500 millibar height higher than normal or lower than normal, looking at climatological normals. And in this case, of course, when you get a trough, it's a lot lower than normal, and you get a ridge, it's a lot higher than normal. So you get these values of differences from climatological values. But in this case, again, just focus on the fact that in this layer at 500 millibars, we look for these troughs and then we look for these ridges. That this basically reflects, and it makes a reflection down to the surface where we see these low pressure systems. We get the storm systems usually out ahead of these troughs, and you get that strong southerly flow out ahead of it, especially at the surface and the veering winds with height. You get yourself a cold front when you get the balance of two different air masses. So that's what we mean by it. That's a broad view of synoptic meteorology. So all of this reflects from the upper atmosphere and all these different layers, and then it comes back down to the surface. And any change at all in these different layers of the atmosphere reflects a completely different scenario at the surface. So as we talk a little bit more about the surface, we can see, like I was just saying, a reflection of what's occurring aloft. So if we have sinking air aloft, we got the high pressure going on, and then we have a low pressure is rising air. So low pressure, since it rotates counterclockwise in the northern hemisphere, that rotation, it's got to go somewhere, which usually is a increase like that. So it's a rise with time. So we usually say different regions of cooler, warmer air masses, or that's going to be bounded by frontal air masses. So you get a low pressure system like similar before, and you get since a low pressure center, I don't know if you can see probably can't see my mouse, probably can there. You see a low pressure center rotates, like I said, kind of like counterclockwise. You get a lot of warm, southerly, moist flow coming in from the Gulf, and that can meet with different colder air mass back behind the low pressure system, which is going to be cooler air. So you get that clash in air masses. And that typically happens right there on that cold front where we typically see that. So again, it's very interesting how this actually combination works. Different magnitudes, different strengths of ridging aloft can cause different strengths and ridging at the surface. And same with the low pressure center. Different magnitudes and amplifications of troughs in the mid levels can lead to different strengths of low pressure centers at the surface. Very complicated and very difficult process, which gets into synoptic meteorology and why the schooling is really hard hitting with this. So really, just generally speaking, that's what we look for. And then if you have a storm system similar to this, as I just mentioned before about the boundaries, we got the cold air and the warm air out ahead of it, like I just explained, and we have that cold front going across. So real quick here, I just want to make sure that everything is sounding okay with the questions. Yeah, okay, everything's going good. By the way, keep the questions going too. If you happen to have a question, drop it off there and I will definitely get to it. And especially if there's anything I didn't explain thoroughly enough, I will go back and make sure that you understand it. So if there's anything that just, well, that didn't quite click what he just said, or I want to learn a little bit more about it, drop a quick question and we'll go over that shortly. So there's different boundaries, like I was just talking about: cold fronts, warm fronts, and even what are called occluded fronts. And what are the difference between the three? Well, cold fronts, probably pretty basic if you've understood this before. It's just going to be cold air that's racing into a region with warm air. It's denoted with what are called kind of like a blue color on a map with these kind of these triangles, or what we call pips. If I want to call, they're called pips on a map. So that's going to be cold air rushing into a region of warm air, which then causes lift, and you get lift along that front. So this cold, dense air, and you got warm, less dense air, basically acts like a ramp, and it ramps up that warm, dense air up into the troposphere, which is already cold. If you're introducing warm air into the cold atmosphere, you're really causing a lot there, and that's usually what we call, that's based out of, that's instability. We're getting displacement of warmer parcels into a colder environment, and we'll go over that more in detail coming up in just a quick moment. We got the warm front, which is a little bit different from that, but acts a little bit different in a way. That's the advancement of warm air into cooler air. And now with that, it's a little bit different because since now we're talking about warm air overriding cooler air like that, typically we see a little bit more of a frontal region, which is it's not as sharp. You can see there in that chart right there. You can see it's not as sharp of a definition there. That's why we don't typically get widespread severe weather outbreaks for warm fronts. They're mostly confined to cold fronts because that cold dense air really has a tendency to ramp up that warm air faster. So with warm air ramping up on top of a cold air with a warm front, we get what's called isentropic lift, which don't worry about the terminology, but it's just basically a slow upglide of warm air on top of cooler air, which usually we see stratiform rain in that. And it's really not typically, we don't typically get severe weather there. It's not impossible, but we don't typically get severe weather associated with a warm front. And there's also a cold front as well. A cold front, it's just basically kind of like when the warm front and cold front eventually merge together, and really you're just talking about very cold air racing into cool air, and you're getting a lot of frontal lift that's being suspended into that region. So usually a very stable environment is where we're talking about an occluded front there. Not typically a region for severe weather. So we're going to be really focusing when we're talking about severe weather forecasting, focusing on that cold and warm air clash along a cold front. So with that, we're going to move into the first poll question. Here we go. I'm going to give this a try. Hopefully I did this right. So this is interactive. Let's see. Okay, they do look like they loaded. So this is interactive. If you have this on your computer, you can actually vote real quick on this. And this is poll question number 1. Now I'm going to have to change the slide to this. So remember the question as I show you here. Where do we typically experience widespread severe weather from a storm system? Now, some people who may have a pretty good understanding of meteorology are probably rolling their eyes. They probably already know a good answer, but these questions are going to vary. Some of these are going to be difficult. Some of these are going to be very easy. So I'm going to select it and launch it, which should change your view. And what happens here is that we should see responses. And yeah, feel free to vote. It's multiple choice. Obviously, there's only 2 choices here. Where do we typically see it now? Where do we see it in the warm, unstable air mass ahead of a cold front, or in the cool, stable air mass behind the cold front? So feel free. We'll finish it here in about a few seconds. Get pretty much a very good participation here until I decide to stop it here. So very good responses so far, and we'll go ahead and close it. Let's see if I see. Then I can share it. All right, yeah, cool. There we go. So, okay, a large majority thinks the warm, unstable air mass instead of the cool. So a few said cool, unstable air mass, and that's fine. And let's see if we can go back to sharing real quick. Well, let's see if we can go back to. There we go. All right, all right. So I was like, I can load it, but I can't show the screen. Okay, there we go. So we should be back to the question here. So that was the responses that we had. So now we'll go to the answer. Warm, unstable air mass out ahead of a front. And that's pretty much the combination of warm, unstable air and cold air approaching from a cold front helps to, like I just explained, lift that warmer air into cooler air above the ground. This causes thunderstorms. And where we're talking about what regions, right there. That would be, as a forecaster, as what I would do when I see a synoptic map like this, a surface map, that's the area where I would look for, pretty much the primary area for severe weather. So in that region, that's where we get these squall lines and we get these strong thunderstorms, sometimes even severe. So usually it's along those cold fronts, not always along a cold front. Now that can vary based on different wind patterns or different environmental patterns. That's the difference between a squall line and a supercell. Now we're going to go a lot more into that too coming up, but it's not always directly on the cold front. It could be either on the cold front or out ahead of it, depending on the environmental conditions. So let's actually go straight into poll question number 2. What are the 2 main ingredients for severe weather? Again, they're going to vary with time to time with the difficulty here. And we're going to launch this one. Again, we're talking about what are the 2 main ingredients for severe weather. And I'm not looking to trick anyone here. This isn't like, okay, well, what about this parameter? And again, there's a lot of different parameters to look at when it comes to severe weather potential. There's even some that are associated with other choices, but I'm looking for the 2 main that are included in the potential for severe weather. Looks like we got getting some very good I will admit one thing. I think there is one of those that's a little tricky now that I look at it. One is like, okay, well, that's pretty obvious, probably not. And when I was like, I look at it now, I was like, well, it's a component, but it's not again, the whole question here is the main ingredients here. So, okay, we'll close that up and share it. See what we can show. Okay, a lot of people, instability, vertical wind shear, very good. And then a few did moisture and topography. And honestly, that's the one I looked at it and I was like, because those are components. I hate to say this, topography less to an extent, but you can have topography cause and influence the severe weather, and then that combined with moisture. But the whole point of the question here was actually looking for the two main ingredients, which a lot of people nailed it. That's instability and wind shear. So let me go ahead and get back to the sharing screen, which should pop up. There we go. We want to make sure everything's back up. All right. And again, I'll remind one more time, yeah, if you got questions, keep them coming. I love to see that there's questions piling up here. So yeah, like we said, instability and vertical wind shear. Variations either in either or. So we can see an increase, more instability, less vertical wind shear, or the other way around. Completely can change the environment completely. We get that a lot down here. We get what are called, if you've either ever heard this term, low instability, high shear environment. And that's a tricky one. That's when there's not that much energy of the thunderstorms, but the shear is off the charts. And sometimes it really doesn't take a very energetic thunderstorm to get it to spin enough to create a small tornado. We get those a lot in the wintertime down here. And we get to the summertime, we get the other side of it. We get more instability and less vertical wind shear. And that's because we're just so hot. And it's really hot, really unstable. We don't have as cold temperatures in the upper atmosphere, but it's cold enough to create, like what you're seeing to the left, thunderstorms. And we get them all during the day. We get those pulse thunderstorms all the time. But the combination between the two, that's where we get a little bit more vertical wind shear and more thermodynamics or more instability, is in the fall and spring months, where we're seeing that clash of the air masses. But be aware, of course, we can get severe weather any time of the year, but the changes or the types of severe weather can change throughout the year. So this is going to be very complicated. I'm going to be very, very thorough as best as I can here about what parcels are and what we're talking about when what instability is. So instability, when we say instability, is the tendency for air parcels. So when I mean an air parcel, it's just a piece of air. Just think of like a square, like just a hypothetical square of air. So we're just talking about molecules in this air. Instability is the tendency for air parcels to accelerate when they are displaced from their original position. Either the tendency to be accelerated upward or downward. All of that is some form of instability. So it is a prerequisite for severe weather. The greater instability, the greater the potential for severe thunderstorms. So you see in this example to the right, an air parcel is imagined as a bubble of air. So I just said a square, it could be a bubble. It's just any type of random shape. It doesn't matter. It has no definite size, and it can be assumed that to retain its shape and general characteristics as it rises or sinks. So there's no entrainment, no changes of this environment. So we're just talking about this parcel, let's say they're rising or sinking. When the parcel near the surface rises, caused by some type of forcing, either by warming of the surface or a cold front coming through the region, that parcel is going to rise. As it rises, it expands and cools as it's being displaced into a region of lower pressure aloft. So it's moving, because remember those pressure changes. Since it's moving into lower pressure, it expands and it cools. So we consider the ability for parcels to accelerate upwards as instability, or what we call unstable. So that's moving that air parcel upwards into the colder area, so it's warm, and then it cools due to its environment. That cooling is instability. So you're displacing warmer parcels into a region of cooler air. Now, it's completely opposite the other way, going down. You can actually take that parcel and sink it down. So a parcel might also sink given synoptic scale subsidence, like a high pressure system, or like sinking air from a high pressure. So that's high pressure that's being sinking down, and that causes compression. So that compression warms as the parcel moves down from a region of higher pressure to a region of lower pressure. Excuse me, other way around, from lower pressure to a region of higher pressure, getting close to the surface. We can think of it diving into a swimming pool. It's compressing it. As an air parcel gets down, it compresses. This process of sinking is called stability, or stable air. So we have instability, which is rising, and then sinking, which is lowering, like that. So one way us meteorologists can identify the processes and the winds and the thermodynamic profile, the temperature and moistures of the atmospheres, we can look at what are called skew-T diagrams. There's a chance you may have seen this before, what a skew-T is basically. They're basically just a vertical moisture and wind profile that's either generated from balloon soundings. So balloon soundings, when we let go of the balloon here at the office, it's got a little device on it that is measuring the temperature and the humidity as it goes up into the atmosphere. How far it departs from our office as it goes farther up aloft is detected from a GPS signal. So if there's very high winds and that balloon is going to really travel down, it's calculated due to the distance changed in the GPS position. We'll then calculate by saying, well, that's 50 knots. If it's going straight up above you, it may turn a little bit. That's a little bit less of a turn with the GPS position. That's winds of 5 knots. So how far it tracks down its journey as it rises will tell us the wind speed. And as it continues to rise up, it'll tell us the temperature and the humidity, which then is calculated into the dew point. So in the graph you see to the right, that red line going up, so that this is the exact same thing like I showed you before. That's the surface at the bottom, and then you're going up, and each white line is different levels of pressure in the atmosphere. So you got 850, 700, 500, 300, 200, and 100 getting towards the troposphere. So we can actually see with this graph the temperature change as it goes aloft. Now, what makes it a skew-T, let's see, that's the next slide here. What makes it a skew-T, now, first I want you to kind of look at what it is. Now, there's a lot of complicated parts of this diagram I'm showing here. But think of it as just a graph. I mean, we all know graphs. We've taken geometry, graphs of an X and a Y axis. Pressure or altitude decreases up the Y axis. So you're going higher up aloft like I just explained. The surface, as you see there, is at the bottom. And then that goes up aloft. So you're getting less pressure as pressure decreases as it increases in altitude. The X-axis going across on the bottom part of that screen is temperature. But the temperature is actually, that axis is actually skewed over a little bit. So that it's skewed to the right a little bit. It's because if it was just an up and down axis, the temperature profile would be more skewed to the left. You wouldn't be able to see it. So instead what we do is we clock it a little bit towards the right. So you see that these lines that kind of tilt left and right like that, they tilt left and right because we're skewing it over. And that's where the term skew-T comes from, because you're skewing the temperature lines. So let me explain that a little bit better. Say like you want to know what the temperature is at a certain level. You would find the 0C here, and you would go up the line to find out at 700 millibars, it's -3 Celsius. So let me go back and show you again. So what is the temperature at 700 millibars? You remember, the axis is skewed over. So you would go up it until you intersect 700 millibars, and it's -3 degrees Celsius. Again, it's skewed over like that. We want to know a little bit further up. Let's say we want to know the temperature at some of the upper levels, say 300 millibars. We'll go and find the temperature there, and we will climb up it to 300 millibars and find out the temperature at 300 millibars is -42 degrees Celsius. That's very cold, like we were talking about before. So we use this, and this is a very good tool. This is a tool that for meteorological, like all the classes I've taken, I could probably draw one in my sleep, but we look at this so many times because different thermal temperature profiles aloft mean different things. If the dew point, as you know by now, when the dew point and temperature are close together, that's 100% humidity, or at least very high humidity in that case. And very high humidity causes clouds aloft. So when you have areas where that dew point and temperature meet like that or gets close together, we get clouds. So when there's a lot of moisture in the atmosphere, it's just pouring rain outside. Well, it's going to be what we call a very moist sounding. So it's going to be very humid all the way up to the top of the troposphere. Or if it's a beautiful day like it is today, that temperature and dew point profile is going to be further apart. So it's going to be drier. So we're not going to get as many clouds there. So this tells a great story. The whole point here is it's a fantastic tool that we can use to make the forecast. We also have there, as I showed you before, the wind barbs. Wind barbs tell us wind shear, or the change with wind speed or direction with height. That tells us a lot. That tells us how, if storms develop, if they'll be rotating, if there's a potential for tornadoes or anything like that. That tells us a lot there too. So again, we have wind barbs, temperature, and dew point, and we can help determine exactly what's going on in the atmosphere. So piling that all together, now that we have a great way to basically, like I said before, summarize what's going on in all layers of the atmosphere, we can identify severe weather parameters based out of this. This can give forecasters a better idea of the degree or the magnitude of severe weather risk. So what I mean by that is, let's just draw this is hypothetical sounding to the left. So I'm going to kind of have to go through this here. Let's pretend hypothetically with the sounding to the left that we will rise a parcel from the surface aloft, something like acting on a parcel. So now we know where the temperature is on here. So I don't know if you can see my mouse here, but this is the temperature. Now, if you rise a parcel, it's going to be, again, we're introducing, of course, it's going to be a lot warmer to the right. It's warmer than the environmental temperature. So what happens there is the parcel will rise, it will cool and moisten, reaching the cloud base and continue to ascend. Since the parcel remains warmer than the environmental temperature, it will continue to rise due to the air density differences until it hits its head. It'll hit its head on the tropopause because it warms there. Now the parcel is cooler than the environment in that case, so it actually then, it doesn't go any higher. That's the tropopause. Instead of now being warmer than the environment, it switches, it's cooler. So as you see in that diagram, it kind of hits its head in a way. And that's where we mean why the clouds no longer rise anymore. So, but the degree of that area that you see there, that colored area, the difference, or I'm not going to get very depthful in the mathematics here, but if you've taken some calculus, you'll know what I'm talking about. But the integral, or the summed area between the parcel's temperature in the magenta and the environmental temperature in the red is where we can actually identify or quantify parameters like what we call CAPE. Or CAPE, essentially just convective available potential energy. Again, it's that area that we see in a sounding like that. This just gives us the ability of understanding the how much energy a thunderstorm has. So the cooler the atmospheric temperatures and the warmer the surface, so we got a big temperature difference from the surface to aloft. That's going to cause a lot more energy because you're rising a lot warmer parcel into a lot cooler environment, which means it's going to accelerate really fast. So that's what we mean by CAPE, or convective available potential energy. So you probably heard this term before, you may have come across it before. Now the same goes for if there's the opposite. If the parcel is cooler than the environmental temperature, it's going to do what we said before, it's going to sink and compress. And that's where we call it SIN, or what that means is convective inhibition. It basically stops a parcel from rising. So anywhere in that blue area, we're not getting rising anymore. It's actually sinking. But so when we look at a sounding like this, if you've seen one like this before, that's what's called a cap. If you've ever heard that term, a capping inversion, is that when parcels are trying to rise, which it's warm at the surface and they're trying to rise, they can't get above that cap, or what we call cap and SIN is pretty much interchangeable. So we have that SIN there, so it can't go any higher. So we can't get thunderstorms. It can't tap into that good energy, that cold air aloft, until that cap breaks, which can happen sometimes. When the cap breaks, that's when thunderstorms have the ability to just completely rise up really fast and reach the tropopause and explode in development. So you'll get cumulus clouds. You'll get clouds that look like they try and rise and then they fail to rise. And you'll get some cumulus clouds in an environment where you have that SIN involved, but where you get that cap to erode and you get that CAPE, the parcel to get into a better, cooler environment aloft, you get explosive thermodynamic or explosive thunderstorm development. Now, of course, this can be viewed a little bit differently. So I showed you the complicated way first, but now I'm going to show you what we see it in a 2D plane. We could see this in using surface map or analysis maps like you see here. This is one from the Storm Prediction Center's mesoanalysis page, which it can get, of course, you get overlaying parameters, so it can get a little bit tricky on your eyes, especially when you have those wind barbs there. Those wind barbs are just surface winds. But you see in the red contour is CAPE, values of CAPE. This is quantified CAPE aloft. And then you get the areas of blue, which is you get an overlap of contours, that's convective inhibition. So this can kind of give us an idea of where there is a cap and where there's not a cap. And if there's not a cap, how much instability is there? So if we see, like for this example here, talk about Macomb, Mississippi, that's an area we could say there is a region of nearing 2,000 joules per kilogram CAPE. That's a lot of energy aloft. And there's no SIN. So all you're looking for here is a lifting mechanism. You got to get something to raise those parcels up into that atmosphere. If it does, it will sustain itself because we have a lot of instability. And in this case, it could have been a front that's approaching. If a front approaches and a cap erodes, that's fair game. You're going to get a lot of thunderstorm development. However, if you're, for example, say you're off the coast of southern Mississippi, we have 500 joules of CAPE, but a lot of SIN. That means there's no thunderstorm activity going on there. There's really little in that case going on in that activity. It's going to take a large change in the atmosphere for there to be something that changes there. Either the cap's got to erode or something's got to change there for there to be thunderstorm development. But like I said with the example, Macomb, Mississippi, that's where we'd be like, okay, we got a front approaching. We really got to see her because the cap has eroded, and we have a lot of instability, and we're looking for something potentially significant. Now, talking about wind shear real quick, to determine the potential for organized thunderstorms, and that includes storm modes, that includes cells, squall lines, etc., even tornadoes. We have to closely analyze the vertical wind pattern. Wind barbs are displayable on skew tees, and of course, if you haven't seen a wind barb, we're going to talk about it before, what it means in a way. It's the change of wind direction is known as directional shear, like we said before, and the change of wind magnitude is known as speed. It's known as speed shear. So we have basically different types of shear there. So usually what happens is typically a lot we get both. We'll get change of shear and magnitude and direction aloft. This example to the right, this is a good example of 0 being the surface, and then each 1, 2, 3 is kilometers aloft into the atmosphere. We're getting that veering. So that's what I would call a veering or a turning with the wind with height and increasing in magnitude. That is a directional and speed shear in that case. So what is a wind barb? This is just a quick one-pager lesson on what a wind barb is. It just shows the wind direction, which is indicated by a long shaft, basically. The shaft will point to the direction from which the wind is blowing. So that example to the bottom left is a north-northwest wind. So that wind is blowing from the north-northwest to the south-southeast. The middle example is the northeast. So that's blowing from the northeast to the southwest. So that's what we mean by that. Each one of those little barbs, a half a barb is 5 knots, a full barb is 10 knots. 4 of those is 40 knots, and then by that point it becomes a flag, which is 50 knots. And then you can go in intervals after that. A flag and a smaller half line is 55, a flag and a full line is 60. And it keeps going therefore after. So usually a circle denotes calm winds. But again, we use these wind flags or these wind barbs when we're looking at winds aloft and sometimes even at the surface as well. So we go back to the example we were talking about before. We noted southerly winds at around 10 knots right above the surface. We see that turns where it veers with time due to large scale lift, which is common in an unstable air mass. And in this transition from time, from this lower surface to the mid levels is what we call veering with wind. So we call it veering when it turns from left, or excuse me, it turns clockwise. Veering is turning clockwise. Backing is turning counterclockwise. Veering usually is an unstable air mass because we have southerly winds out ahead of maybe a low-level jet. So we got that wind shear going on aloft. The opposite of that happens in a front because you still have those that winds aloft from the southwest, but now the winds are from the northwest or something like that. So now the winds are turning counterclockwise with height. If they're turning counterclockwise with height, that's backing, which is indicative of a stable air mass. So we get the backing behind fronts, we get the veering ahead of fronts. The degree of veering can quantify that based out of the degree of wind shear, and that can be quantified based out of different values, what we call bulk shear or like a different layer shear. We can do a layer calculation between maybe 0 and 3 kilometers and call that the 0 to 3 kilometer bulk shear, which is the average shear within that region. So very interesting tool, very helpful for us to understand how storms are going to form and the storm mode. So talking real quick, we're going to talk about how that impacts thunderstorm development. Well, it greatly does. Typically in the summertime, with the example to the left, we have almost no vertical wind shear. It's very low, but we have a lot of thermodynamics. So we're getting a very warming surface that's being billowed up into the atmosphere. But if there's no vertical wind shear, you're not going to get any displacement of that vertical motion. So what happens is all that motion comes up, and what comes up must come down in that same spot. And that's why we get pulse summer thunderstorms. They build up and then they come back down, and then that's it. And then you're done for the day. You just get what's that little outflow boundary that comes out. So that's just a density difference between the warm air and the cooler air that fell back to the surface. And then that boundary could pop a new one, and then it pops right back on itself. But if you introduce vertical wind shear, you're now taking that updraft that goes up and you're displacing it to the right. So you get, again, just enough veering direction, just enough of change in wind direction or wind speed, you can get rotating updrafts. So with that can lead to the development of more sustained mesocyclones even. So that's usually what we see as organized. Now that we don't have all that energy killing itself, so it doesn't just kill the storm back when it collapses. Now you have the energy coming up and it's being displaced and coming down in another portion, and you get the cycle. So you get no interference with that updraft anymore. You get all that lifting up, and it keeps lifting because it's depositing somewhere else. And you get the cycle. What happens is you get longer lasting storms. So when we get this shearing aloft, these storms can last a lot longer and sometimes even become severe thunderstorms. So we can quantify, like I showed you here. This is a bulk shear. The example here to the right is the 0 to 6 kilometer bulk shear value here. It's just the essentially just it's a very complicated way of doing it. I'm not going to get into the math, but it's if you know about vector subtraction, yeah, trust me, don't worry, I'm not going to talk about that. It gets very complicated very quickly, but we can quantify these the magnitude and the directional change using these values like you see to the right. So that tells us a lot there. So you see higher of levels of higher shear up toward the north, say like up in north central Alabama, meaning there's probably going to be more coincided with thermodynamics, means there could be stronger thunderstorms there. Less shear across Louisiana. So it's a very complicated balance between the two. So, and that's what basically, that's what we mean by throwing it all together there. It takes, it's important to remember that it takes a large combination of a very large amount of calculated atmospheric parameters to determine the degree of severe weather risk at hand. And that's where we come in with analysis, like I just showed you. I just went through a very quick slideshow of tons of parameters. I'm not even gonna talk about what each one of them are. But while adequate instability and vertical wind shear are the main ingredients, be aware that even the smallest amount of instability in a region of very high wind shear can lead to small tornadoes, like I was just saying. And sometimes just an overwhelming amount of instability in a region of little vertical wind shear, we can still have strong to severe thunderstorms. But all these create different types of modes of severe weather that can vary all throughout the year. So it's a complicated process. And I just wanted to kind of show it to you without actually going into the definition. I wanted to show you the definition of the CAPE and SIN. And I wanted to kind of just briefly go over bulk shear. But I can't, this class will be hours and hours and hours long if I went over all these other different instabilities, different wind shear there. And that's why if you're interested in more training, please check out weather.gov/jetstream. If there's anything that I did not quite cover, if there's something, oh, well, I wish you would have covered, there's a value called the lifted index or the total totals, the sweat index. I could keep going and going. There's tons of them. And we use these tools. But if you want to learn more and you want a little bit more of an in-depth understanding of this process that I explained, please go here. It's free to make an account and just kind of do your learning at your own. And you'll be able to kind of cover some of that I didn't quite go over. So really quick, I'm going to go over the numerical models. Which, as we know, weather is caused by atmospheric motions that can be described in mathematical equations. And that is way too comprehensive for humans to calculate, especially when you see a map like that to the right. The map to the right here is a North American 500 millibar vorticity map being looped over the next 380 or 240 hours. This is from the GFS model, the Global Forecast System. So it's just too complicated to quantify this by hand. So we let computer models do the work for us. Numerical weather prediction is used. Basically, that's what we mean by that is modeling the atmosphere of both motions horizontally and both vertically. So we try to interrogate these models by basically investigating potential biases, the errors that help create the forecast. Now today there are countless amounts of models. You've heard them all. There's the HER, there's the NAM, there's the GFS, the Euro, the UCMET. The Canadian, you probably heard these terms before. We're not going to go over every single one of them because each one of them have their strengths and each one of them have their weaknesses. But just know that these are very important tools that we use as forecasters. And of course, you can't take guidance as gospel. You cannot take model guidance. It's just a tool that we use. And we really try not to show and portray model guidance that often here in the office. Now we do occasionally sometimes if we want to show simulated reflectivity by some of the short range models to kind of give an idea that, hey, there's going to be a squall line coming across the area later today. But really those are tools. And there's like, think of a mechanic. A mechanic has tools and there's different tools you could use. How many tools are there that exist to take off a tire or take off a whole wheel? Well, there's tons. You can use an air ratchet or you can use a wrench. You could use a torque wrench. There's tons of them. I'm a car guy, so I made that example. So there's tons of different examples that you can give on this. So these are just tools and we use these. It's breaking these down and determining the biases between the two, which maybe one model's had a tendency of being too wet, or it's been off lately, so you can't really trust it much. And then it's basically the combination between the two helps determine what the forecast is going to be. So that's what we do here at the National Weather Service. We use this model guidance, and we have some great software that show this model guidance. And if you've happened to ever hear this term before, that's called AWIPS. It's a software analysis package that stands for Advanced Weather Interactive Processing System. I can never remember that all the time, but there it is in front of me. Now remember, the data that we use, and a lot of people don't realize this, a lot of people think we use all this top secret technology. No, actually, not really at all. The data that we use is actually not private and is available to be used to the public. You can access this data. We have it downloadable. You can download it in what are called GRIB2 file formats and use meteorological programming. You got to have some good meteorological programming skills to do this. I do this at home. I have my own servers at my house where that's because I'm a weather nerd, where I like to download the data and pre-process or process it out and to create my own weather maps. It's a very fun hobby if you're into programming, especially meteorological analysis. And I can do this at home. I can create the same maps that we see in our office. We can see them. I can make them at my house. And you've probably seen weather websites out there before, and that's what I'm getting to here, right here. There's a ton of different websites out there. Colors Your Page, NINSEP Mag, which is the model analysis and guidance page. Plenty of other public websites out there. I can't promote them, but like Pivotal Weather, Tropical Tidbits, Weather Bell. I think that one you have to have an account for. The Storm Prediction Center, HREF, which is a model ran at the Storm Prediction Center. Even historical analog guidance exists too. There's so many right there at your fingertips. So if you're as eager as I was getting into meteorology and you want to learn a lot about this and this excites you, go to Google, type in tropical tidbits, and it'll take you to a web page. It even has a tutorial on how to use it. And go through the guidance, check it out, go up and down through the atmosphere. That's how I got into weather. I would come home from school and I would go to the INSEP model analysis guidance page back on its old primitive days, back when we had the ETA model and the RUC model, which was back in the day. I may not be as old as others are, but I remember that as a kid, and I remember that's how I learned. I started just going up and down through the web page and be like, oh wow, this is interesting. I could predict severe weather 13 days out. Well, let's watch it for trends. Don't take it literally, but just watch it for trends. It could be a signal. So, take a look at it. Check out some of these web pages. I basically listed, these are some of my personal favorites. That's why it's actually in here that I use. And sometimes we got this in-house, but you can use it yourself. And of course, stick with the experts. Check your local National Weather Service office. SPC convective outlooks, local news and broadcast meteorologists, local news and broadcast meteorologists do an absolute fantastic job helping us to message some of the forecasting, even severe weather warnings that we put out. They do a fantastic job, great partnership, and we love what they do. Check us out. We got a local National Weather Service forecast and also Storm Prediction Center convective outlooks as well. So next is going to be moving into radar meteorology, but before I get into this, because it gets pretty hot very fast, and I can see I'm coming up, I'm timing myself, coming up to 58 minutes. I'm going to have to kind of, hate to say this, but speed through a little bit of the radar basics so I can get to the meaty portion of the radar meteorology 2 coming up here in just a little bit. So I'm still seeing, I'm getting a lot of good questions coming in. I'm going to kind of see what we got here. I'm going to pop it out just to see. Okay, yeah, awesome. We get a lot of good questions here. Keep them coming. I can't answer them quite yet, but when I get to the break, I'll definitely be able to do that. Let me put them back there. I can see them on my screen here. So we're going to jump straight into radar meteorology 1 here, and this one's going to be not that long. I want to spend, like I say, more time into the dual pole portion of the presentation. So this image I'm showing you here, this is a very, very, very cool loop here. And actually, let me go back because I just absolutely love this. This was recorded. This is a Doppler on wheels. And if you're wondering what you're looking at, actually, that is the Hook Echo. That is a tornado. And not only that, if you got a good eye, that's a sister tornado to its left being absorbed into the circulation. That's from a research Doppler radar on wheels that recorded this nearby a tornado. So the colors are different from a conventional radar to the left, and then velocity you can see to the right. You can see that couplet, but look at that other couplet that came into the top left. That was actually that's actually the eye of the tornado there. You can actually see it, and then another tornado got wrapped up into it, a satellite or sister tornado you've heard before. Anyways, I'm geeking out over that because I think that's just such an awesome imagery. So Now, understanding the basics of radar meteorology. So Doppler radar, simply just the fact that radars emit a beam of energy that are just radio waves that strike an object in the atmosphere, and it is scattered in all directions. But some of that energy is reflected back to the radar. Now, the larger the object, the greater the amount of energy that's being returned to the radar, and that gives us the ability to see what is going on. So we can see raindrops or anything in the atmosphere. Now we can actually identify if it's seeing a bigger object or more objects in one radial scan. That's just one beam going out. Or we can see less or more. So we can see different amounts, density, or the size. So either we're seeing a lot of droplets or not many, or we're seeing big droplets or small droplets. The amount that it's seeing, the size or amount, can be determined the difference between these radar colors. That's lighter colors is just simply that. That's usually lighter rain. That's less amount of precipitation and smaller amount of raindrops. You can get bigger amount of raindrops or bigger amount of rain in one radial scan, and that's the brighter colors that you see there. So that usually gives us an idea of rain rate. Now, here's a caveat with that, though. That's just telling us precipitation. What about hail? The radar doesn't know the difference between seeing hail and raindrops. At least base reflectivity does not know the difference between seeing hail and raindrops. It thinks it's the same thing. It's just, hey, I'm seeing something here. It's something large, and there's a lot of it. So I'm going to come back with it by saying it's a very bright color on reflectivity. So it's simply that. So, but there's other caveats as well. Remember, the Earth is curved. Hopefully you know that. So the beam is not. The beam goes out in a straight line. So when the Earth curves and the beam remains straight, the beam increases with height as it gets further away from the radar. And even close to the radar, as you see here with this example, you got the tornado on the bottom and then the mesocyclone in the middle part of the atmosphere. We're most of the time seeing the mesocyclone when we're identifying a thunderstorm. Even when interrogating a tornado warning, we're interrogating the mesocyclone. So as it gets further away from radar, sometimes we're cutting way above the thunderstorm, or sometimes we're cutting way above the mesocyclone. And unfortunately for down here in Southeast Louisiana, we get a lot of shallow thunderstorms. What I mean by shallow is it's not really deep with height. They're very low to the surface. So the mesocyclone is really low. So when they're very far away from the radar, we don't even see the mesocyclone. And unfortunately, it can cause very difficult problems trying to issue timely warnings. And that's just one of the challenges with being down here, is that we don't typically get those really big supercells you see out in Kansas and Oklahoma. We instead get the shallower ones here, which can be a little bit easier to detect when they're closer to the radar. But to give you an example, if you know our WSR 88D located in Slidell, we're talking about like Point Coupee Parish and getting up towards like Wilkinson County, Mississippi, beyond Baton Rouge, including Baton Rouge and beyond. It gets a lot more difficult there because there's a radar gap. We have Slidell here, and we have LIX in Slidell. We have Lake Charles, and then Fort Polk, and then Jackson. All of those are so far away from that middle point. So it causes a little bit of difficulty. We get severe weather there. So that causes a challenge for forecasters like myself and others here in the Weather Service office. So we got to take that into account. There's a caveat there with radar. Also, what's called the cone of silence, which as the radar scans across, it's surveilling across. It's shooting these beams of energy out, these radio waves, and it comes back. It scans at one certain level, and then it goes up and scans another level, and then another level. And it keeps going up about as high as 19.5 degrees. It doesn't go any higher than that. So what it looks like is this same image that you see here. I'm now going to show what an interpolated 2D slice would look like. So of course there's slices, it's seeing this. So this image is interpolating, which is just connecting the image between the areas where there's blanks of what the radar looks like going up. And we have what's called the cone of silence. And this only occurs right next to the radar. So as you see, you got the surface on the bottom, increase in height above ground as you go up. And it creates a problem. And this is an example from Lake Charles when the tornado, or this was a tornado that went almost pretty much directly on top of the radar. What do you do in that case? I mean, you can't tilt up, you can't look higher, tilt to loft. You're only looking at the lowest, but now the lowest is within the radar range. It's within the cone of silence. We have to use neighboring radars in this case. Well, I know where neighboring radar would see higher up a lot, but hey, at least it's something, and it becomes a little bit of a challenge for us. So other features with base reflectivity, main features, the hook echo. You probably heard this term before. It's in the region of a supercell where tornado formation can occur, and I just circled it right there. It's usually on the south or southwest side of a supercell. That's typically, depending on the cell orientation and shape, can differ. The key to remember is that the presence of a hook echo does not mean a tornado is on the ground. You got to remember that. That just means there's rotation in that level. So some spinning is going on in that storm enough to pull the precipitation around. So that can occur in the mesocyclone portion of a thunderstorm, aloft. But we don't know what's going on at the surface looking at radar, almost never, using base reflectivity. So keep that in the back of your mind. Again, if you're analyzing radar and you're saying to yourself, hey, that's got a hook echo, it's got to have a tornado warning on it. And we get those questions a lot. People are like, hey, there's a hook echo. Where's the warning? That doesn't mean anything. There's a lot more to it. We got to look at the atmospheric environment. We got to see if there's atmospheric environments conducive to tornadoes. If storms are elevated, which is a term, meaning that there's just a lot of cool, stable air at the surface, but it's unstable aloft, which means they're spinning, but a tornado can't extend and stretch down to the surface. That happens actually sometimes down here as well. So outflow boundaries or gust fronts, they could become identified on radar when there's low-level air density differences. Like I was talking about before, when the pulse summer thunderstorm, all energy comes up, and what comes up must come down on the same spot. It creates an outflow boundary, which is just a cold downdraft air, and you get that warm upflow in front of it. You can get what's called a roll cloud. That's typical. You can get that sometimes, even what looks like a shelf cloud sometimes even as well. So that's something that can happen as well. And what it looks like on radar, I absolutely love this radar imagery because this came out of the terminal radar from Memphis Airport, I'm assuming. But this actually shows those density differences. Now, this is a 2D plane, okay? Let me go back because it's not a looped image. This is a 2D slice. So we're not seeing these storms come up at you in the picture. So that you can't see them grow up. But when they grow up, they come down and they splash back on the surface, this cooler air. So that density difference between the cool air and the warm air creates these really amazing looking boundaries. And when you see some clashes, like right there, right in the middle of the screen, boom, you get a thunderstorm development there because you get that clash of air masses and it's squeezing that warm, unstable air. Well, it can't go down into the ground, it's got to go up. So it forces it up. That's what we mean by forcing. And you get a thunderstorm development when you get two boundaries interact. And it can be chaotic in some instances, and it's very hard to forecast it, or at least nowcast it, meaning at the short term. But because you can get thunderstorms and boundaries all over the place, sometimes you get explosive development, sometimes you won't get any at all. But it happens a lot, especially during the summer months. Three-body scatter spike. I briefly went over this in the basic course, but that's just the effect of where the radar beam strikes hail. It goes back. Actually, it bounces off the hail because hail's typically spherical or spherical in nature. It bounces off the hailstone back to the ground, back up, and then hits back to the radar, and it shows it back downstream as a false signal. So what it looks like, I'm gonna jump to the next slide, or actually, no, this is all the same slide. It actually looks like a false signal down radial. And that's a very good indication to us that there is significant or large hail at that level of where the radar is scanning. That doesn't mean that hail's making it to the ground. It's just telling us that there's actually hail at that level. Because remember, the radar beam increases with height as it continues aloft. So if we're looking something way down the line, something way far away, and we're scanning it where hail is forming, it can create this three-body scatter spike and spike its way outwards. And it could tell us, wow, there could be some severe hail. The question is it making it to the ground? Because these are hailstones in a very cold atmosphere, but when it comes down, it's coming into a warmer atmosphere. So there is some evaporation with time. So if I recall correctly, I think that's sublimation, maybe. So it's basically it eventually changes with time. So, oh no, that's actually evaporation, my bad. It changes with time. It's basically a solid that changes, and what it does is it basically would melt as it continues down towards the surface. So a TVSS does not mean that a storm contains severe hail. It does not at all. So interrogation must be performed to determine the likelihood of severe hail if the environment is prime for hail to reach the surface or anything like that. So TVSS is also something to monitor for on radar. Radial velocity, we explained this too earlier, that radial velocity is just simply the measure of basically what we're seeing, what the radar sees, what motion is it moving towards the radar or away from radar, or perpendicular to the radar? Which way is it moving? Well, warm just means that it's moving away towards the radar. Green means towards. The brighter the red, the faster away. The brighter the green, the faster towards. And those two together, especially in a thunderstorm, in a position of a thunderstorm where you get a rotation like that, where there's a supercell or a hook echo, yeah, you got yourself a tornado or the potential for some type of a tornado. So that's what causes what's called a couplet or the change in wind direction, and that's where you can get that tornado. Now remember, as we just said before, since the radar beam increases with height, we can apply this to radial velocity to determine the wind direction with height. And remember, we got these range rings here. So as the radar beam, think of like the radar beam's like a cone as it goes aloft, okay? It's like a cone because it's scanning higher, higher, higher aloft as you go further away from the radar. So say like that middle cone is 1,500 feet above ground level, and then further out is 4,000 feet above ground level. So the beam is increasing with height. So we can see a bunch of red and greens, but those red and greens are at those levels of that cone. So as you get way far out there, you're seeing velocities aloft. What can we do to determine? Well, actually, we can use that to see the wind pattern. So if we draw a line, for example, now we know that red is away and green is towards, and it's going to change as it gets higher aloft. So you follow that gray area color, that gray part, which is the perpendicular part, like that, and you can actually tell us that there is actually change with winds with height. So at the surface, now hone in just towards the middle, very small towards the center part, you get the greens are from the right and the reds are towards the left. So from the southeast to the northwest. So at the surface, we have what we call southeasterly winds. So there you go, southeast winds at 5 knots. Now at 1,500 feet, so now look at that bigger ring. It's different. Now the greens are in the bottom left part of that ring, and the reds are towards the top right, bottom left part of the ring, and the reds are in the top right part. So the greens are coming from the southwest and moving towards the northeast. So that big ring there is now turning. So now at 1,500 feet, the winds are from the southwest. And this is even more tricky. Now at 4,000 feet, it's a little bit more to the left. So now we're saying winds more from the west-southwest towards the east-northeast, something like that. So it changes a little bit. And now we can say at 4,000 feet, we have west-southwesterly winds at 30 knots. So very interesting that we can use velocity to tilt up and see the wind change in direction with height. So quickly, it can let us know that this is actually a veering wind profile because it's turning like that. It's turning from southeast to southwest. That's clockwise and veering, which means usually an unstable air mass. So just looking at one radar image, one velocity image, you can say to yourself, it's an unstable air mass. So of course, now we've seen this term before. You've probably seen base and storm relative velocity. What is the difference between base velocity and storm relative velocity? Those are two complete different products, but we're going to go over one before the other. Base velocity is simply just what we just discussed. It's just showing the targets of motion, the radar beam in a given location. It's useful to determining areas of strong wind from downburst or detecting speed of a cold front. So it's just simply just that. It's just the motion of what's occurring. The caveats, though, is that the strength of the wind will always be less than when the wind is blowing perpendicular to the radar beam. Now remember, green is towards, red is away. Well, what happens when the wind is blowing perpendicular to the radar? That can cause some problems there. It becomes lower values, or what we call the grays that you see in that blinking image there. The grays are perpendicular. We can't really get a good view on what exactly is going on there because the wind is blowing perpendicular. And it can be perpendicular in any direction. It can be green towards and then away, or perpendicular and then away. So anytime it has to be perfectly away or perfectly towards to see those greens and reds. But when it's going either perpendicular to the right or left, it doesn't matter the direction, it just happens to be perpendicular, we get those grays. And that can be a little bit challenging for us. So kind of give you an example of what we're talking about here. In this hypothetical example, the radar is in the center and the actual wind flow is identified by the black arrows. So that's exactly what I was just talking about. You got the radar and you see just focus on the black arrows for right now. So you got the radar and you see number 6 there. The wind is coming directly at you. So that's green. And then number 2 is going directly away from you. That's red. So remember, radial velocity only measures if the echo is moving towards or away from radar. Like I said, there's a degree of error, points 1, 3, 5, and 7. Those are the corner ones when being viewed at an angle. Comparatively, of course, notice that points 8 and 4, where the wind is perpendicular to the radar. Since again, the radial velocity only measures when the echoes are moving towards and away from the radar falsely identifies this region as calm or near zero, when in reality it's not. It's just gray, or that gray or white area. So it can be a little bit tricky using base velocity, and it kind of give you an idea of what this looks like on radar. Very realistic example here of a squall line or a messy squall line approaching us from the northeast excuse me, northwest, approaching us. So you see at our radar site, we got the greens towards the radar and the reds away. So we got a southwesterly wind occurring here. So we have a southwest wind blowing towards the radar site, which is right there in the middle of both screens. But as you tilt further up aloft and the lines coming at you from the northwest, they're all towards the radar. So that's obviously strong winds associated with a line of storms. And as it progresses through the radar site, you see that it's almost all green. But look at that top right arrow there. That's actually showing some grays. And you know the winds are probably equally strong there as it is towards middle parts of St. Tammany Parish. We got a lot of greens there, but as you get up towards the top right, it becomes a little bit of a difficult issue. Also, the bottom arrow too. You see that transition from green to red because it's becoming perpendicular to the radar. So it can be a little challenging. And as the line continues to push all the way through, you can see that it turns into that green to red. So now we got the green wind, that's winds from the northwest to the southeast, but we still have that problem where it's perpendicular, where it turns gray like that. So base velocity has its challenges basically. So now we're talking about base versus storm relative velocity. There's a problem with base velocity when identifying circulations in motion, because circulations in basically a mesocyclone in a storm is it's a spinning feature and it's moving. So we got a problem with that. That's something that's spinning and moving. We're going to have something that's going to match right. So what we mean by this here is look at a bottom graph here. This bottom image here is that you have a mesocyclone circulation plus its storm motion means that the resultant flow pattern is going to be a lot higher when you have that addition. So you have the addition of the two bottom arrows that makes for faster motion. But the left motion plus the right motion subtracts each other and you get a slower motion. Complicated, yeah, I know. So let's show you what I'm actually talking about here. This is a base velocity image of a hook echo. This is a rotating thunderstorm with a mesocyclone that was just south of Lake Maurepas. Now, what we're talking about here is that, well, if you notice, where's the reds? Isn't a couplet supposed to be reds and greens? They're all basically just about all green. So I don't understand, is this a couplet? Well, what's happening here, this is where the area I'm talking about, while there's a very still noticeable couplet there you can see, and it's co-located within a hook echo region, the inbound values are largely overcalculated. And with the outbounds actually switched in direction a little bit. This can make identifying areas of rotation very difficult task when using base velocity. So you're looking for areas of rotation using base velocity, not best recommended. You can still do it, but it's not a real good trick there. So this is what I'm talking about, is that the inbound is 79 knots and the outbound is not really an outbound. It's actually still inbound at 6 knots. So this is so confusing. Is this rotation? I'm not sure. This almost seems like very fast winds on the bottom half and not so fast winds at the top. But here's the trick. Here's what we could do. We can use what is called storm relative velocity, which subtracts out the storm motion, and it becomes a color like this. That's a lot easier to see. You got the bright reds and you got the bright greens. So the good news is, like I said, we can subtract out the storm's forward speed and to see this true rotational velocity of the mesocyclone. Think of it as if we are making the storm seem stationary. And that helps you understand it. That helps me understand it. Is that we can actually think of the storm stationary, and we're just singling out that circulation itself without the motion being in it. So we're seeing the true rotational velocity occurring within the storm with no influence to the storm's motion. So again, there it is. And what we see instead, 41 knots inbound, 29 knots outbound. A lot easier for your eye to interpret that. Like, okay, there's an obvious couplet. So this is what we use when we're actually trying to determine if a tornado warning needs to be issued, if we're analyzing a storm couplet or anything like that. We see those reds and those greens using storm relative velocity, not so much base velocity. So, and that's what I was just talking about, storm relative velocity. We have subtracted out the storm's motion to better see the true rotational velocity of the mesocyclone as the effect of it being stationary. It is, we have determined, the useful trick of that is determining true mesocyclone rotational strength, like I just talked about, and it's much easier for us to interrogate. However, the caveat is that different radar system software either will average out a mean storm motion or SRV, and it requires radar operator to frequently update the storm motion and speed, especially if the storms are moving at different directions and speeds. So it takes a very keen eye. You have to be very up on the radar at all times to determine what the storm motion speed and it being subtracted out. So you're seeing a reflectivity image there. There's base velocity and then storm relative motion. You can kind of really singles it out there a lot. So Now, talk about other base features with base and storm relative velocity. One's actually a very good one. Now remember, once an updraft of a thunderstorm reaches the tropopause, it can no longer climb any higher aloft in elevation. You can see it here in this image to the left. I love this image because it seems like a very good aerial view of a supercell thunderstorm. You can see where the updraft is, and then it can't go any higher than the tropopause, and it spreads out and it creates an anvil. But you see that little bubbly feature there where the tip of that arrow? That's what's called the overshooting top. That's where there's so much upwards forcing of that updraft. It pierces the tropopause and actually bubbles up a little bit into the stratosphere. And that's, again, called an overshooting top. So we can actually measure. So when it hits the troposphere, it spreads out from that updraft position. We can measure the resultant energy spreading, what's called storm top divergence. So hypothetically speaking, say that the radar's to the left here, and it's going further aloft at height. So the radar beam goes higher off because of the curvature of the Earth. But if we tilt high up enough to scan it, yes, we can actually scan into this part of the thunderstorm and scan what's called storm top divergence. So remember, green is towards and red is away. So we're seeing that splitting feature there. We're actually seeing that middle part that's splitting away, and that's storm top divergence. And that's used, we can measure this by adding the intensity of the inbound velocities and the outbound velocities, as most studies have calculated that around 70 to 120 knot storm top divergence is enough to sustain hail growth. So this is actually a very good tool for us to use to determine the potential for hail and sometimes even damaging winds too. So we're seeing a very strong updraft, which is telling us that, wow, there's definitely something going on here. We need maybe to monitor for the potential of a severe thunderstorm. Another feature with base reflectivity is the mark signature, or that means the mid-altitude radial convergence signature. This is just kind of the opposite of what I just showed you. Instead of the spreading out, we're getting air that's actually descending, and when air descends, it has a tendency to collapse. So instead of the spreading out of air motion, now we're seeing the convergence. So instead of divergence, we're seeing convergence, and it's coming together basically. Usually we have to, like I say, look for regions of convergence in the mid-levels, trends that increasing convergent magnitudes yielding increasing confidence of downdraft potential. And what does that look like on radar? Well, here's one right along a squall line. You see those reds and those greens. So red's away and green is towards. So all that's not going up, that's going down, because you know with a thunderstorm, all that motion's pushing down. So that's telling us that there is kind of, just think of it as like just like you're pouring water out. The motion's going downwards and all that air is going out to the surface. So a very interesting feature. There you go. There's a better representation of what I just meant there. Those two arrows coming together, there's a representation of a mark signature, mid-altitude radial convergence. And there are tons of other base radar products available out there. I'm not going to go over every single one of them, but you've probably heard of VIL. It's a primitive product not frequently used in warning decisions. It's just not as really good as we have a lot better tools these days. However, it still serves a really good quick interpretation of the vertical continuity of reflectivity without having to go through all tilts. So it's something we still as meteorologists will kind of look at, but it's not really used much in warning decisions anymore. Echo tops, spectrum width, plus many other derived products available. Of course, we're not going to go over with this talk. They are available and Jetstream or with MetEd if you would like to know more information there. So we are now moving straight along into radar meteorology 2. This is the meaty part of it. It gets a lot more interactive as we continue through. So we'll get through a little bit more as we continue through this, continue through the talk. But I just want to kind of just go ahead and dive right through radar meteorology 2, see how we're doing with questions. Looks like we're doing really well. All right. And that everyone's hearing me really well, still powering through this. So thank you so much for joining, making it this far. Y'all, you are all troopers. I appreciate you joining me with all this, and I'm trying to go through this as clear as I can, but at the same time, be sensitive to not make this to be a very long talk. So going to go straight into radar meteorology 2, and this is the fun stuff. This is now, as you see with that image in the background, we get a lot more information now telling us about the thunderstorms, not just velocity, not just reflectivity. And it used to just be like that. Not only maybe 10 years ago, probably a little bit more than 10 years ago, that was just about all we had. I remember specifically back in the April 27, 2011 outbreak, the one I remember that one extremely well, being in Birmingham. At that time, they were only using, we didn't have dual pole at that time. We only had reflectivity and velocity. And it's a relatively new technology, and we're getting a lot more used to it in applications. And it tells us a lot more about what's going on. So talk a little bit more about it. Now, traditional radar is to your left. That's the old National Weather Service WSR 88D, shoots one horizontal pulse. That's all it does. Now, latest technology now is that we send to the right here, what's called dual polarimetric radar. We're transmitting a horizontal and a vertical pulse. So think of it like, it's as simple as this, a little crosshair of a horizontal and a vertical pulse is going out. So we're sending a crosshair out basically like that. So now we can actually tell you information about drop shape, the correlation in the change in shape. There's tons of different information that we can look at now. That we now know more about a vertical and a horizontal shape. We can now talk about if there's more of a vertical versus a horizontal, or there's more horizontal versus a vertical. That could tell us things like, is it an ice crystal? Are they oblique spheroids, which is just another fancy word for pancake shaped raindrops, or just really wide raindrops. So we could do all this really cool information. So as a result, like I said, you see here, we're sending out that kind of a crosshair, and you can see in that example, we can see snow. We can see hail now. We can see the drop sizes of rain. We can see if the raindrops are just more spherical, like small raindrops, or fat and oblique, like a big fat raindrop. And they can tell us a lot of different things like that. Very, very good tool. So first, my favorite is correlation coefficient. Correlation coefficient provides a measure of the consistency of the shapes and sizes and targets within the radar beam. So simply, the higher value shows that there is higher consistency in the size and shape of the radar targets, while the lower value indicates greater variability in shapes and sizes. So I think actually I have that backwards. I'm not 100% sure. This is a value basically from 0 to 1. So a solid value of 1 means that the orientation of the vertical and the horizontal pulse match really well, and there's no chaotic motion going on. That's typically raindrops. So if you see in this example, that's raindrops you see coming around. So that's like a cell out ahead of the line, and you see the squall line that's approaching from the left. So that's very high in correlation, which is a good indication that the raindrops are all the same. So it's likely raindrops. But if there's a lot of changes, if there's more horizontal than vertical, or it's changing a lot, that's what we mean by a lower correlation. So we have a low correlation between the horizontal and vertical pulse. That can be a lot of different things. Like in this example, if you've heard of ground clutter is just like bugs, anomalous features like birds, planes, things like that. They're chaotic and they move a lot. So correlation is going to be very low in drop shape. So it lowers it down to a blue color. So very cool tool, because now we can actually see raindrops and things that are not raindrops. Because if you've probably seen it before, when you have so much ground clutter that we can't see the difference between rain and ground clutter, now we can see what is rain and what is actually ground clutter. So this is a very good tool and can be used for a lot of things, including tornado debris signatures. Probably one of the more important, probably one of the biggest applications, especially for our area, is that these tornado debris signatures. Because debris is just like ground clutter. It's, in a way, it's chaotic. There's debris being flung around in different directions and different shapes, lowering the correlation, which means that it's going to come out as a blue shape. And this is another Doppler on wheels look at a very classic supercell that you could see the tornado there as that blue ball at the hook. And that's that lower correlation, and that's all debris being thrown around. So all the reds you see there, those higher, brighter colors, is good correlation, meaning it's just raindrops, all going not chaotic, just basically all within the same beam. So very applicable in using things like tornado debris signatures. Now remember, again, we cannot see what's going on at the surface with radar, so that's why these tornado debris signatures are extremely important. That's actually, for the first time ever, we can have confirmation on what's going on at the surface with a tool that only views that up in the upper part of the air. So debris, when a tornado drops and it spins up and hits trees, picks up leaves, pieces of homes, everything like that, sprays it up into the air, sometimes gets far enough to where the radar beam can slice into it and see it. It tells us there's an actual tornado on the ground. So now we can actually call radar confirmation and tornado warnings now. An amazing technology, and it's still more research is growing day to day on it. Other things too, since, as you know, rain is typically very consistent with pattern, size, and distribution, like I just mentioned, values will return high, which means good correlation, values near or at or above 1. However, if you introduce rain and snow mix, you have less variability, meaning correlation lowers. That's sleet and even rain snow mix in areas on radar. However, plain snow is typically very consistent with pattern, size, and distribution. It can return higher values as well, But with this information combined with surface observation data, we can actually determine where there is likely rain, snow, or rain-snow mix occurring. Now, of course, keep in mind that, however, that these estimates are typically higher aloft, especially the further you get from the radar. There is some discrepancy sometimes. So you can see in this example here, you see you have rain to the bottom, sleet, snow, rain mix causes that lowering in correlation because you have drops and shapes in different sizes. And this snow actually, due to the fact that they're typically around the same size, okay, if it's just plain snow, it can actually show a higher correlation as well. So it can help us determine where the freezing line is if we don't have a very good observation system of where that 32-degree line is. So we can use correlation coefficient to determine where rain and snow is occurring, which is an even extra added plus. Now remember, we were just talking about three-body scatter spikes. Since that's a false signal shooting down radial of the hail aloft, it comes back as anomalous. And if it's anomalous, it's non-meteorological. And if it's non-meteorological, it's going to come back as something wild and crazy, something like a lowering of correlation coefficient. So this phenomenon helps create these spikes down radial of hail, and it creates these false signals. So if you have base reflectivity up to the left like you have, and you have correlation to the right, and you see that little bit of a spike, so you know you see a hail core based out of base reflectivity, which is that white circle there. That's pretty obvious based out of the brighter colors. But you see that little bit of a spike behind that hail core, you go, I can't tell. Like in this example here, I can't really tell if that's just rain or it's just a jutting out area, or is that three-body scatter spike. Switch to correlation coefficient. It will confirm the presence of a three-body scatter spike, which will help with your warning decision process. And of course, you can determine a lot of different things too. You got rain, hail, graupel, snow, ice crystals, melting layer too, and even debris, as I have there, biological targets. There's different things like birds and anomalous propagation. Not going to get into all of that. But this is stuff too. I'm not going to go through all this, but it's just kind of, this is a good guidance here. This is available on training online, but this is kind of a good guidance level for you to kind of understand what we typically see with different types of hydrometeors across the area. So again, this is what I was talking about before when I meant by you can't tell the difference between ground clutter and precipitation, which happens a lot down here because we get a lot of biological scatter because we have a bunch of bugs in the summer. So sometimes precipitation, if it's light enough and the biological is dense enough, they can kind of look the same when you can't really tell the difference. And that's why you can see on the right image, you see the difference between that biological scatter, which are those bugs, and then the precipitation, which are the higher values, which helps us determine what's the difference between the two. And now, a product I also love just as equally as correlation coefficient, which is called differential reflectivity. Now, this is a very useful product to help depict the echo size and shape. And this is called, again, differential reflectivity, or we call this from this point on ZDR. So ZDR is just a fancy way of just saying differential reflectivity. This one, using the graph to the left, now we're seeing that, again, that crosshair. If the horizontal and the vertical is equal, you get a value of 0. If the horizontal is larger than the vertical, you get a positive value. If the vertical is larger than the horizontal, you get a negative value. So it's ranged in a scale from -13 to 20. So the lower you go, the more the different vertical differential. The same with the higher the value, the wider it is. So what do I mean by that? This will help you understand. We got focus on the middle part. 0 is spherical. As you go higher, it's the wider it is. When you get lower, it's the taller it is. So, okay, that's weird and kind of cool. What kind of help is this? Well, this can help us identify hail. This can help us identify very large raindrops. This can help us identify ice crystals aloft, especially in the upper part of the atmosphere. So it's actually extremely useful. This is a classic example out in the plains, how ZDR can be useful to determine. Of course, this example doesn't always apply down here, but hail tumbles as it falls. It's never just a stone that just goes straight down. And when it tumbles, it creates a near zero ZDR because the radar beam is scanning it, it thinks it's spherical. So you see in this example, it thinks it's a sphere. But that's not always the case along the northern Gulf Coast, as we typically get hail when it's mixed with rain, causing ZDR to be noisy or a low bias. And this is a perfect example here where noisy ZDR around that occur here. Like I could circle, whoops, I thought I could circle it there, but you see that brighter reflectivity, but where's that lowering of ZDR? We don't have it. Well, if you were just to use that example I just showed you, you'd say, well, there's no tumbling hail here, so there can't be hail. We had a 3/4 inch hail report that followed right after this. So Doesn't typically happen here because it's usually water coated. We have a lot of water with the hail. We have so much moisture along the northern Gulf Coast. So not always a good indicator for us, but it's a very good indicator for the same as correlation coefficient when it comes to tornado debris signatures. This is, again, not always a fixed value is required, but since debris is tumbling, same as hail, it wants to return a near zero ZDR value. So you kind of see it there, of that lowering there, which helps confirm the presence of a tornado. So you combine CC with ZDR. So now we're going to go back to TDSs here. There are several conditions that must be met to clearly give meteorologists a confident answer to what may be occurring. Once a region of low CC has been identified, typically it will be accompanied with a region of higher reflectivity. Remember that base reflectivity only sees object size and not the horizontal, and cannot depict the difference between rain and hail and debris. Remember that. Of course, it will come back as a higher reflectivity value. It doesn't know what it's seeing. Thus, base reflectivity will typically see debris as higher value. So we got that as check mark number 1. So connecting this with regions of lower CC, now you must be in a region of cyclonic, or very rare cases, anticyclonic rotation using base velocity. So you got the hook, you got the rotation. That's great. Now you got the lowering of CC co-located with that higher level of reflectivity, because the reflectivity is telling us it's debris. The correlation is telling us this is some wild and crazy things going on here, so it's got to be debris. The ZDR is telling us that it's near zero, which means it's got to be some type of debris. Those are 4 true tale signs that we can use to determine that this is likely a tornado on the ground from a product that's only scanning aloft. It's actually incredible, this type of science that this is that we're being used here. So now there's other dual pole products that are available, ones that go way more in depth that are fun to say, but I'm not going to explain. KDP, which is specific differential phase. That one helps with determining regions of increasing drop concentration, like heavy rain, and can aid in flash flood detection. PDP, not useful. That's differential phase shift. Don't want to get into that one. Hybrid hydrometeor classification, which just tells us basically a best guess of the echo type, because as you can see now, we can determine what's snow, what's rain, what's sleet, what's grapple, what's debris. Now hydrometeor class can actually average out what it's seeing by giving us just one fixed value, which is actually very helpful too. Plus many other dual pole products that are available that we're not going to get into. Wow, we made it. Basically, the hard part of it is over. We made it through. Now it's going to get a little bit faster. It's going to be a lot more interactive. We got a little bit more pulse coming through. We're going to actually now talk about supercell structure types and methods, and we're going to go over a lot more things here. So this is my puppy Laddie, who's definitely no longer a puppy. But I think he is now maybe 6 years old. But I've raised border collies my whole life. This is my 4th border collie I've raised, and I raise them and train them for agility and for obedience. And this is Laddie, certified puppy SkyWarn storm spotter, telling you to remember to keep your eyes to the sky and to the ground. So we'll take a quick break. Let's do, if I got the time, it's 7:36. I'm gonna make this a little bit quick. Let's get back by 7:40 because I want to address some of the questions that we had. So grab a drink, anything you need to do to kind of refresh, stretch your legs out. That's probably what I'm gonna do real quick. And then we'll meet back here at 7:36. We'll meet back at 7:40. So we'll go ahead and pause, and then we'll talk back with you in about 4 minutes. All right, I'm showing 7:41. All right. All right, well, go ahead and get back here. We're going to check out some of the questions we've had. I'm going to try and get to them. See if I can get them to pop out. There we go. All right. Oh, wow. A lot of great questions. Very good. Let's see here. I'm going to go through each one of these. We got some very good questions. I like these. Okay. Yeah. Okay. These are more comments. I like these. Can radar see particulates overshooting tops of the troposphere like that from causing a mushroom cloud? I'm not sure. Similar thing occurs in mushroom clouds. I mean, radar can scan. It can scan anything. It's absolutely incredible the things that radar has scanned over the years. It can scan volcanic ash. It can scan, it can scan anything. Military airplanes that produce those fine particulates, it's called military chaff. If you've ever heard of that, which is actually a tool, something that these military jets, when they fly over, they drop these fine metal pieces, little metal fragments out of their airplane to scramble enemy aircraft radar, to confuse enemy aircraft. It's actually very common military practice that they do off the coast of the Gulf of Mexico. And we can see that sometimes. Correlation coefficient will pick it up as a low value. So it's extremely interesting, the amount of things you can see on radar. You remember back when Columbia, the Columbia shuttle disaster happened. Oh gosh, I can't remember the year. It was early in the year. I can't remember it, but that was a time, of course, we didn't have dual pol back then. We just had base reflectivity and velocity, but that one, it broke up over Texas, and what was left of the debris shot down towards Louisiana, as it was, of course, the path of Columbia was to continue down towards Cape Canaveral. So it was entering the atmosphere over the western United States, coming down through the south central United States, and then over Louisiana. When it broke up over Texas, what was left of the debris actually flung over Louisiana, and we actually saw a brightening of the debris. We actually picked it up on radar when it happened. So there's absolutely amazing things out there that we can see through radar all the time. But yeah, we got a lot of good comments. I like that too. That's fantastic. Good comments coming in. Like I say, you got questions too. Keep them coming. But it looks like everything's good here, and I'll get back to them. If you have anything else, any other questions, definitely let me know, and we'll kind of go ahead and keep powering through from here. So, all right, now we're in part two, a little bit more interactive, a little bit more fun. Now that we got a little bit of a root there, we understand model analysis, we understand layers of the atmosphere, and then even more cool tools about radar meteorology and how to use them. Now we got a little bit more. Now we can focus a little bit more now on supercell structure. So let's see if I can go ahead here and talk about. I love this looping image. That is just that is the coolest looped image there. Of course, it's not looping the whole way. It looks like it just stopped all. But sorry, I saw another. Do we get a copy of the slides to keep studying from? You absolutely can. I have them available in PDF form. Of course, they're available in PDF, but yeah, I use a lot of really cool animations and things like that, so they won't be maybe as good. I'll try. I know I created a PDF version of the basic course, and I had to go through and take all the animations off. But for this one, I'll do the same. I'll definitely go through and do the same with this one. And if you want that, now at the very end of this, you will get a certificate, and you'll have my personal email address too, my work email address. And just shoot me an email if you're interested in it. Just say, hey, I got the certificate and I'm interested in the slides. I'll get it to you as soon as I can. And we've had some people who wanted to have the basic one, and we went and I got that one taken care of too. So I'll do the same for the advanced, so you can have it. It'll be a PDF form, so it'll be something just to go over, and I'll get that to you as well. So yeah, like I say, more questions, keep them coming. I love it. So I'm going to go back because I just got to see that supercell. That just looks incredible. So that's a mesocyclone right there. That's a spinning mesocyclone over the plains. We just don't get a view like that down here. We just got way too many trees and a low cloud base. That's a lot of that dry air entrainment they get aloft. So they get the dry air that comes off the Rockies, and it usually causes that dry air entrainment. So you get a really good view, like a transparent view of what a mesocyclone looks like out in the plains. And you get these views. But here, imagine like that cloud base, basically where that dark color is rotating and lower, and then you don't see that. And where's the mesocyclone? I don't even know. It's just you don't get that view like you get out the plains. So supercell structure. Thunderstorms, especially supercell thunderstorms, present a wide variety of dangerous hazards, as we know. We're going to go over now. Now, remember in the basic course, I briefly went over the different hazards. There's a front flank downdraft, the rear flank downdraft, the updraft, the inflow notch, and there's tons of things. Here now we're actually going to go over each one of these in detail. And as you can see in this graph, there is a lot of things going on here. That kind of looks kind of crazy, doesn't it? Well, that's actually about how much, like the image I just showed you before, this is about how much that's going on. So much violent vertical motions, ascending, descending motions, different cloud types, different threats like tornadoes and hot hail and high winds. All of this are going on in a supercell thunderstorm. And I love to show this example because this is one I believe is one of the most classic radar signatures of a tornado that I've ever seen, the May 3rd, 1999 Moore, Oklahoma tornado. And so it's just a beautiful flared out anvil, and they get the tornado at the bottom. And weirdly enough, you can think of like the supercell almost kind of like a low pressure system. There's fronts. There's a frontal boundary in front of the forward flank downdraft, a frontal boundary in front of the rear flank downdraft. And then you have the warm, moist inflow going into the tornado, which is typical out ahead of the cold front. So you think of that low because a tornado is almost like a low pressure center in a way because there's so much rising motion that you get a lowering of pressure. But you get a cold front and another cool front there and the warm air coming into it. So there are two downdrafts to focus on. The forward flank downdraft, which is where all the heavy rain and the hail is occurring, and the rear flank downdraft, which is a lot of, you get actually a lot of that motion that comes up out of the tornado has to come down, and it comes down out ahead of it, and some of it actually comes back down and rotates back around it as the rear flank downdraft. But the rear flank downdraft can be extremely dangerous, believe it or not. And this can be kind of a surprising feature. Sometimes people don't even realize that a rear flank downdraft can have winds over 100 miles per hour. It can be just as dangerous as a tornado. I remember specifically November 24, 2001. Here I go with dates again. I can remember tornado dates like birthdays. And I was a kid, and I remember, well, I was a teenager at the time, and I had a multi-vortex tornado go right through almost into my backyard. And the tornado passed. Not a big deal. The trees were moving and anything. And as I was inside, I was outside the house, and I got thrown inside the house by my mom naturally. And when I was inside the house, I noticed just the trees. I had a tree fall in my front yard. Just the house just felt like there was a hurricane outside. And I think I was about 13 years old at that time. And I wondered to myself, what was that? That wasn't the tornado. And what hit my house was the rear flank downdraft. We had over 100 mile per hour winds go through my house, even though the tornado missed us. So there are other associated threats you got to watch for, and especially if you're out there storm chasing. So what does it look like? Usually in a classic sense like this, especially if like a rain wrap tornado, it's going to be that drying you get on the backside. But unfortunately for here, again, we don't have that dry air entrainment in the mid levels. So sometimes a rear flank downdraft can be in disguise, and you can still have precipitation on that backside. So typically you want to look for the wall cloud and tornado right there where there's a rain-free base, but be aware that there's not always a rain-free base there. So other structures out ahead where the potential tornado would exist includes the forward flank downdraft, and that's the hail core. And if you're out there storm chasing, or if this tornado is approaching you, realize that hail core could obscure your viewing very very quickly. You can be in the hail core, and within seconds you're in that tornado, and you don't even realize it. You can't even see it coming. So it's a very dangerous part of this thunderstorm that all you got to look for. So we have different things, different supercell structures that we are going to mention here. One of those is the updraft, and an associated portion of that's identifiable on radars called the beware. And it sounds a really cool name, but I'm going to show you, I'll tell you what that means in just a second. But you got the warm, moist air coming into the storm, and remember, you got that updraft, and it pierces just a little bit into the anvil, or past the anvil, past the tropopause, and creates the overshooting top. So that flat part here I don't know if you can see my mouse, but that flat part is the tropopause. That's the entrance of the tropopause. But that warm, moist updraft is so strong, it actually pierces through the tropopause, like I explained before, and creates a bubbling, overshooting top. Now remember, we have vertical wind shear because we have supercells. Now vertical wind shear helps create supercells. These supercells last a very long time because there's all this wind shear going on. So it's tilted forward. So all that air goes up and then comes down, sometimes out ahead of it, as a cold downdraft, as heavy rain and wind gusts, strong winds. You also have amble lightning, which is of course extremely dangerous as well, and the flanking line, which is some of that air that comes back around it as a rear flank downdraft. Now we can actually see sometimes an updraft. Believe it or not, you can see an updraft on radar where you think to yourself, well, that's just rising air. It's not, how's that happening? Well, if the air is rising, it can sometimes displace the precipitation and create what's called a BWER, which is now a name, or we'll start with a WER, or weak echo region. BWER is a bounded weak echo region. And this can create a really cool, like, little hole on radar. And this is a good example. This is one recently, March 17th, 2021 in Wilkinson County. This was an EF0 that this was one that I personally put the warning out for. I remember this storm very well. And you see there, well, how can you see it there? You see that little donut hole there in reflectivity? That's a part of where the updraft is piercing through and actually creating a donut hole. So it's almost like a completely occluded hook echo in the mid levels. So that little hole there is a good indication that there's strong rising vertical motion and good rotation as well, because you're getting it rotate around a mesocyclone. All true tell signs to there likely being maybe a tornado here. As you can see, you're seeing that the reflectivity bind's a little bit wider here because it's so far away from radar. So it's extremely challenging in this area. But fortunately, we did have a very good lead time on it, although it was a very minor tornado with no injuries or fatalities or anything like that. But at that bounded weak echo region was one of many reasons that I was thinking to myself the storm was increasing in intensity with a very strong, as you can see, mesocyclone using storm relative velocity, that there was obviously a strong mesocyclone and a good indication that there could be a tornado based out of atmospheric conditions. So the forward flank downdraft forms from what's called water loading, which is the dragging of air downward, basically. So you get a lot of upward motion, and that's a lot of loading of the water in one spot, and all that heaviness has got to come, heavy motion's got to come down. And it melts and it creates this evaporation, which creates a cold pool and an outflow boundary. So the evaporation process, which releases heat, this latent heat release in that type of phase change, causes cooling when it sinks. So, and that's the case when you have that, you get a lot cooler air going down to the surface, and that can sometimes be in the very front part of a thunderstorm. Remember this diagram I showed before. Usually it's not that dangerous, like it's nothing that's going to hit you. You just don't want to be in it. If you're located, like for example, in the middle part of the screen, right near the top of the first arrow near the word downdraft on forward flank downdraft, you see the in and downdraft is the city of Moore. Soon to be, that city was going to get flattened by an F5 tornado. So right ahead of it, they're getting heavy rain, some small hail. Probably there's more hail back to the west, but they were getting, they were never in an inflow region, at least not at that point. But if you were back to the west, you would never even see the tornadoes. So these are the hazards to watch for. Also, hey, can you see an overshooting top on radar? Yes, you can. I mean, certain conditions exist, you definitely can. So this is a two-dimensional slice of a thunderstorm, of a supercell. So you see in the bottom right, that's a very intense updraft, which is causing a weak echo region. So it's keeping and suspending rain aloft. Well, if it's suspending rain into a very cold atmosphere, it can actually help form hailstones. So it actually can create a little bit of a circulation. So how does hail become severe hail? Well, I created this really cool animation that if it keeps that updraft keeps suspending the hailstones larger and larger and larger until the updraft cannot handle the weight of the hail anymore, and it eventually falls. The intensity of the updraft will determine how large the hail gets. So if it's a very intense hail draft, you got very severe hail, large hail. If it's a weak updraft, sometimes small hail. Now, of course, you don't have to have a rotating updraft for there to be large hail, but you have to have some form of an updraft. You have to have displacement, like I was showing before, that warm air into a cool environment, and you're introducing all that moisture into a cold air. But if you have all that moisture being continuously pushed up by a strong updraft, it stays up aloft and it loads up and it becomes bigger and bigger and bigger before it just becomes too heavy, and eventually it falls down as large hail. So, of course, with persistent updrafts and supercells, hail and heavy rain will typically reside away from the hook echo. And classic supercell on the northwest side is mentioned there. So that's where we typically see the heavy rain and hail. Type precipitation gradient is a good designation where the forward flank downdraft is. So there's your front flank downdraft, or forward or front flank downdraft is the same thing. So you get a little bit of that downdraft, but since it's meeting that inflow air, you get that sharp reflectivity gradient there. So that front flank downdraft rarely cuts off the inflow. It almost never does. Instead, it creates a balance, almost like a frontal boundary of warm, moist air going into the tornado and cold, stable air, cooler, stable air being pushed down from the front flank downdraft. So you get a reflectivity gradient there of it being mashed up together, or front. So that's how you know the difference there. And of course, there's your hook echo to the bottom left. What's a mesocyclone? It's a mesocyclone is a rotating updraft, strongest at the mid levels. So you get wind shear, which causes these circulations, horizontal circulations, and with an updraft, these horizontal circulations get tilted up, and then they get into the middle of the atmosphere, and as you see here in this picture, they spin. So rotation develops in the environmental horizontal vorticity, which is what that bottom part of the you see there, horizontal vorticity. It's just that's what happens when you have changing wind direction with height. So that's the veering winds we were just talking about before. Southwest or southeast winds to southwest winds. You get that. Think of like rolling a rolling pin in a way. When you're rolling a rolling pin, you're introducing motion away from the bottom. So you create a roll like that. So you create these rolls if you have these veering winds, which is usually all over the place. You just can't see it. But if you get an updraft, strong enough updraft to tilt that up into the vertical, boom, you got yourself rotation and you got yourself a mesocyclone form. And of course, the parent circulation that could lead to a tornado. So again, kind of the same thing I'm talking about here with the middle part of the picture here. You get that spinning that goes all the way up aloft. So you got a rotating mesocyclone tilted out ahead due to good vertical wind shear. You got the forward flank downdraft in balance to the inflow, and you have the rear flank downdraft that's not over killing the inflow. If you can have this balance just right, you can have yourself a long duration and a deadly situation with a long duration tornado and a deadly tornado with that. So this is an example here, 4-panel radar. Left and right are the same thing. So the left 2 panels is base reflectivity. The right is storm relative velocity. The top 2 is the lowest tilt on radar. The radar's to the right of this image at 2,000 feet above ground level, and the bottom is at 12,000 feet above ground level. So low levels of the atmosphere just above the surface, and the bottom 2 are at the mid levels of the atmosphere. And remember that mesocyclones are much larger in diameter in the low levels than in the upper level, or larger in diameter in the mid levels than it is in the low levels. See the size difference? That's the mesocyclone at 12,000 feet, and it stretches down and tightens up when you get to the low levels, and then you get the tornado eventually on the ground. So that's something to keep in mind. This was the February 7th, 2017 Acres EF3. This was a large and violent tornado. It was actually on the ground. We call this one an EF3 because we actually did not have accessibility to survey where we thought there was an EF4. We actually thought it was EF4 based out of velocity signature, but it didn't hit anything. All it did was damage to trees, and not really a good indication of it being a 4 because it didn't hit structures. It did cross over I-55, but this was one that actually also prompted a tornado emergency for Madisonville as it approached from the southwest. So also, you see there's a little bonus question. You see the Bounty Week echo region to the bottom left, that bottom left image. That's that donut hole in correlation right next to that mesocyclone. So we got ourselves, that's for us here in Louisiana, it really doesn't get that much more classic than that. It's kind of it's a messier supercell, but it still has that beautiful symmetric fanned anvil, a very good hook echo, and then you got the debris signature there too, Bounty Week echo region, and a very strong rotational velocity couplet. You better bet this one required a tornado warning, which of course it did. And there's the Bounty Week echo region. Other structures that exist in a supercell, the wall cloud. Simply put, a lowering, rotating cloud base where humid, rain-cooled air from a downdraft is drawn into the updraft. So usually you get these little tails that stick out a little bit. And it's basically where we sometimes see tornadoes, or most of the time see tornadoes. Now, when I say that tail that sometimes sticks out, this is what I mean by that. This is called a tail cloud. Or you've ever heard the term beaver's tail. There's a rabbit's tail. There's tons of different slang terms for it, but a tail cloud's one of them. It's basically just that's that rain-cooled air that's meeting that warm air, and then it basically is just kind of like the inflow notch going into a wall cloud. A very good indication that the storm is breathing and is very healthy when you see that type of a cloud. And again, due to the low cloud basis, we don't typically always see stuff like that. We don't typically see a well photogenic wall cloud in the distance. And sometimes we don't even see a tail cloud. I've never seen one down here. Most of the time, hate to say it, it's just a low hanging base in a tornado, which makes storm spotting down here very, very tricky. Mammatus clouds forms on the underside of an anvil, is composed of pockets of cool air as particles fall and evaporate. It does not produce severe weather, but may be associated with a strong to severe thunderstorm. Usually you'll see mammatus clouds on the front part of a supercell or in the back side of a supercell, co-located with that overshooting anvil. More commonly, they're in the front part of a thunderstorm, but I've photographed plenty of times where I've seen mammatus in the backside as well. And again, it's just a really good indication that there is a lot of energy going on in the atmosphere. There's a lot of rising motion, and all that energy is making it to the very top of the troposphere, and it is just jam-packed. So that's another absolutely beautiful photo. We get them sometimes down here. You may notice them more in the summer months if we have like a day of very intense summer thunderstorms. It may look something like this with kind of some scattered mixed layer clouds, but absolutely beautiful and amazingly photogenic. So the V notch, what is that? That's a weird one. That's basically a slot of lower reflectivity values that can appear downwind on the edge reflectivity field or the anvil layer, surrounded by high reflectivity values. I'm about to show the next one for this one to show you what I'm talking about. The V notch basically is in the anvil layer. It's when the updraft is so strong and the anvil is being spread out ahead that it actually hits the updraft and spreads away from it. And that right away from it motion, it's almost like, just think of it in a way like a log sticking out of the water. It creates a split flow and it goes around it. The water will go around a log, kind of like a good analogy like that. So you get the updraft and you got it says 9-kilometer flow there. So the upper level flow, and it goes around the updraft and splits out. We don't typically get V notches here that often here. We can occasionally. That's more of a plains thing, but they are definitely a feature that we see sometimes with supercell thunderstorms. And of course, I've already hinted at this one now about 3 times what an overshooting top is, and that's that bubble that you see above the tropospheric anvil layer, caused by very strong updraft. Now, on a very good, like clear, maybe spring, summer, or early fall day, you may be able to see a cumulonimbus in the distance, and you may see a little bit of a bubble on top of it. It happens. Here's actually a really good picture right here of what one looks like. This is probably something that you may similar see if you have a good view. Maybe like if you're down near coastal waters, if you have a little bit more of a flat view and you know there's severe thunderstorms at a distance and you get a view like this, you may see it overshooting top if the thunderstorm is strong enough. It's a very, very good indication of a strong updraft, which can sometimes lead to a severe, or it being a strong or severe thunderstorm. And it can be identifiable from satellite. And I told you already about radar. This is a satellite image of it. You can actually see 2 individual peaks. Well, it could be at this time going on was a splitting supercell, which is actually 2 supercells that split in direction. Not going to get into the details on that one. That can actually happen. There is such a thing as a splitting supercell. And those are 2 individual updrafts, one that goes right of the mean flow and one that turns left of the mean flow. One has a higher tendency of producing a tornado, the other has a higher chance of hail. If you're interested in learning more about that, I can explain that towards the end. So the shelf cloud, this is more typically along squall lines, but you can get a shelf cloud on a supercell as well. This is typically associated with a line of storms, like I said. Low-hanging wedge-shaped formation that occurs along the leading edge. It could be either a gust front or a thunderstorm. This picture here was taken from myself from the office of a squall line approach, and it was a broken line, but definitely was extremely photogenic. And it's a very good indication that there's the potential for gusty winds. I do highlight that potential. Just because you see a shelf cloud does not mean you're going to see severe winds, but it's a good indication that there are high winds somewhere associated in it, maybe above the ground. So if you're chasing and you see something like this, keep it on the back of your mind. You may need to watch for some dangerous high winds. So as a summary of the features, as you can see, there's a lot that goes on in supercells. Any slightest influence or change in the atmosphere, that's the change of the wind shear. The instability, anything that changes can change the storm structure, mode, and intensity. This is the Tuscaloosa tornado, probably another very classic, most perfect image of a supercell I've ever seen. That was at the time it was producing the EF4 tornado in Tuscaloosa, which is just there. You can see the word Tuscaloosa there. Beautiful symmetric fanned anvil. Really, again, just like the Moore, Oklahoma supercell image I showed before, you really don't get any more classic than that. But now we're going to talk about storm mode in motion. And this one right here I like to show was a wild card. This was the El Reno tornado of May 31st, 2013. The path, the image to the left is a loop image of the tornado, which started out as a classic supercell right there. But what in the world happened to it? Almost like the Hook Echo occluded into the mesocyclone, which is exactly what happened. The tornado, that's the track of the tornado on the right part. It became as wide as 2.6 miles wide in diameter. Basically, from what other meteorologists have defined it as, the mesocyclone essentially dropped to the ground. Can that happen? Well, it could, but it's not really well studied. So this was a wild card case, and unfortunately led to the fatalities of a few storm chasers during this day because of the fact that it made such a sharp left turn and became so wide. So this was a little bit, that's why I show this one here, to show that, hey, not every supercell is exactly easy. Hey, that storm's just going straight. They move around, they can turn right. They can get occluded and turn left. There's tons of different motions associated with it, which is usually why when you see tornado warnings, the polygons are a little bit thick like that. They're a little bit wider to accommodate if it can make a little bit of a left or a right movement, because they're rarely just a direct straight line. They may curve to the left and then get cut back up like this one did, get re-occluded into the mesocyclone, or they can reform and shoot back to the right, which sometimes happens, especially in a strengthening mesocyclone. So they can wobble around. They can move around, so we never want to be too specific with a warning. We want to give some room of error in case it does move around, as like this one did. So storms can come in all shapes and sizes, depending on the environmental conditions at the time. The modeling guidance, this was a computer modeling of what a supercell would look like with different wind speed direction and changes aloft. It's amazing, because that's what you see in the top left on each one of these, A, B, C, all the way through I, is the hodograph. I don't know if you probably ever heard of hodograph. It's just a polar coordinate graph showing you the wind direction and speed with height. So each change in hodograph changes a complete different supercell. If you have directional wind shear and less speed, and actually that would be less speed shear and less directional speed with height. So you got more of the same direction with height and less direction change. That's B on the top right. So that's winds usually that are unidirectional, which is all the same direction. Now, if you got winds turning aloft, so it's constantly turning with height, that's A. So you get a curling one. The whole point here is that the smallest variations can change supercell strength and type. You can get them that curve a little bit to the left, or the anvil fans a little bit more to the right. There's a ton of different shapes and sizes that these supercells can come in. So these are hazards that you got to be aware of. So also, like I said, any variation in change, if you have upper level winds that are parallel or perpendicular to the front, usually that's how we get cells that are out ahead of a front a little bit better. Comparatively, if you have upper level winds that are parallel to a front, instead of perpendicular, now we're saying parallel, you can get a squall line. So that wind pattern really matters a lot. When I'm going back to this, that upper level wind pattern means a lot to storm mode, storm structure, and sometimes you may even get the mix of both of them. So it happens, and these are things you got to be aware of too. You can usually get a good indication from this from model guidance, but you need to really be aware that it can usually change. So we're going to open up the poll again to question number 3. This is going to be what is the storm mode in this radar imagery? So this one's going to be hopefully a little bit. Let's see if I can get to this one, number 3. So we're going to launch this one. There we go. What is the storm mode in the imagery that I just showed? It's either going to be, it's a squall line, or is it a mixed cellular and linear, or is it just supercells? So when I say mixed cellular and linear, that's a mix of supercells or just any cells and a squall line. Or was that just a squall line that we just saw? Again, I'll give it just a few more seconds. Wow, this is a tricky one. All right. Okay. Because this one's one that can be subjective, but there is, I would consider this to be, there is a right answer to it. Okay, we'll go ahead and end it here. Wow, very good. We'll close it and see if I can, oh, shoot, I didn't mean to close it. Okay. Oh, wait, no, there we go. My bad. There we go. So, wow, very good answers. A lot say mixed cellular and linear, mostly a squall line, and very little, mainly supercells. So, very good. Let's see if I can go back to the image here, give you the answer. Mixed cellular and linear. Well, what's going on in that image there? We got a supercell out ahead of it, and just north of slide L. So the radar image is at the bottom right. We got a supercell right ahead of it, and it's messy looking, but hey, we get messy looking supercells down here. You see an event like this on radar, that's pretty typical for here. In fact, that's probably a higher end event we would look at. We got a supercell. If I remember correctly, that supercell did produce a tornado, and then we had a squall line coming in. That's more of what we call a quasi-linear convective system, or QLCS. It's just a fancy word for a broken squall line, but it's a squall line and a supercell, which can cause mixed mode threats. We can get a supercell tornado out ahead of it, and then we can get high damaging straight line winds behind it. So, like I said, hate to say it, but we typically get this type of severe weather for here. It does happen a lot. We get mixed modes. It's almost rarely just a squall line. It's almost rarely just supercells. We almost always get these mixed mode events. So the whole point here is that you must be able to confidently identify storm structure and mode and threats to understand where you are in the vicinity of potential of hazards. Simply said, you got to understand storm mode, the direction, the hazards, and trees and terrain. All this is extremely important. That can help you be safe and keep you from becoming impacted from dangerous weather conditions. Always be what I call situationally aware. Always know where you're at. Always know that, hey, if you're going down a road, is it a dead end? If there's trees, I can't see it. Am I getting too close and there's too many trees? I need to back up. So what I mean by storm motion here, I want to jump into this too. Now remember back from the basic course, the best perspective to view rotation was within the rain-free base. You want to be within that. Now say that we do have a classic supercell. That example I showed earlier is a chunky looking classic supercell, but still there was a way you could still chase it. You could approach that from the rain-free base. It did have a very small one. If storm motion is towards your location, you become exposed to dangerous weather conditions. So say that this is your position here near Beta Springs, and this supercell is moving left to right. What kind of view might you have? Probably a very good view of a tornado, especially if you're in a good distance, you're keeping a good distance from the rotation, you're not too close, and you're in a very good vicinity away from trees that is obscuring your vision. Now, remember when I showed you that model guidance there, the different shapes in supercells? Well, what if this day the supercells are shaped like this? And you're here in a Beta Springs and that supercell's coming at you like that? What's that gonna look like? You're gonna be obscured. You're not gonna see the threat until the tornado is directly on top of you. So it's very much important to know you got to be situational aware of your position, where the storm is. You got to be aware of the storm motion, the storm structure, the other threats, including a squall line. I mean, hey, I'm tracking a supercell like the example I showed before. I'm tracking a squall line, I'm tracking a supercell, but there's a squall line coming behind it. I can get trapped with damaging winds if I'm not careful. So always be situationally aware. Don't just be driving out there blindly trying to see if you can get the hook echo or whatever, like anything like that. Just always be situational aware and stay safe. Now, I promised a difficult one, and it looks like this one's going to be somewhat difficult. I'll be very interested. This is the first time I'm showing this question, but poll question number 4 is, now you got a tornado to the left here. Consider a tornado moving northeast at 45 miles per hour. Which side of the tornado would you expect to see the highest winds? Now, I want you to remember back on the difference between base velocity and storm relative velocity. Now, we're thinking of storm relative motion here. So give it about 5 seconds. Look at this. The tornado is rotating like that. Okay, it's rotating counterclockwise. And it's moving towards the northeast. Are we saying you're going to see the highest winds on the southeast side or the northwest side? So remember, moving to the northeast, southeast, or northwest. Where would the hot winds be highest? Let me launch this poll. All right, here we go. Number 4, launch. Now the tornado is moving northeast. Oh wow, there. That's great. I love diversity with answers. That's great. I like everyone to think too. That's awesome. So, and we're going to explain it too. Now this one, yes, there is a right answer to it, but we're going to explain this one too. I'm going to get to. I got some very good graphics and schematics here. Looks like we got very good participation. Very good. Wow. I'm seeing the results come in live here. This is really cool. Okay, we'll end it there. Looks like well, got some changes. All right, we'll go ahead and close that and share it. Okay, most southeast, few northwest. Very good, very good. I like that. That's good. We're going to go over exactly why what the answer is here in just a second. Here, let me go. Whoops, let me make sure the screen is back. It should be back. There we go. And we're back. All right. So, oh, what's the answer? Here we go. Southeast side. And now why is that? Now we're going to explain it. And we're going to explain why the southeast side, because a lot of people wouldn't even know there is a side. You would think to a tornado, well, it's just tornado. What does it do? It's winds that are sucking towards one center point. It's convergent flow. Why would there be a side of a tornado that's got higher winds? Wouldn't it just be equal? That's not the case. Now, consider this conceptual model of a tornado to the left. If a tornado did not move and was completely stationary, yes, you would expect equal winds around our arbitrary diameter of a tornado. So arbitrary diameter of a tornado. So you see that you got circulation. Yes, you'll have 60-mile-per-hour winds, like say around an edge of a tornado, equal because it's not moving anywhere. But this is rarely the case. Tornadoes are rarely stationary. Tornadoes have a forward speed, and sometimes the same as storm speed. I mean, they can vary, but most of the time they're the same as storm speed. So we're going to do this little fancy graphic here. Say we have this same tornado as before, 60-mile-per-hour winds within it now, but say it's moving east at 40. As it shoots across, we are adding, remember before, just like the base velocity and storm relative velocity case, we are adding 40 miles per hour to that one side because it's moving east at 40, but then we're subtracting 40 miles per hour from the from the adjacent side because it's kind of canceling each other out. And what you end up getting is 100-mile-per-hour winds on the southeast side and 20-mile-per-hour winds on the northwest side. So that's another danger to look out for. This does actually happen. Now, when you're within the tornado itself, it's going to be creating damage, of course, but I'm talking about the range outside of a tornado, just shortly outside of a tornado. You get those 100-mile-per-hour winds where the tornado winds are strongest, of course, there too, plus with the rear flank downdraft. If you're within the vicinity, that part of a tornado is extremely, extremely dangerous. So keep in mind about that. Tornado motion, this is something that I learned in college, actually. I remember this specifically. It's something that I didn't really think about before. I was like, wow, you think of a tornado, it's all relatively the same distance and everything, but it's not the case. Storm motion has a big factor into tornado speed. So now we're getting towards the end here of the tornadoes, water spouts types and myths here. Boy, this one's absolutely incredible because when I talk about myths, people talk about, can you have two tornadoes at once? Oh yes, you can. You can definitely have two tornadoes. This was a very, very famous one. I remember this one very vividly, watching this on radar. This was the twin tornadoes in Nebraska, June 2014. I was in college at the time, actually, getting ready to graduate, and saw this on reflectivity, which was just absolutely just breathtaking. I've never seen anything like that. I have the image here, what it looked like. Those are two tornado debris signatures and two couplets right next to each other. Now, of course, we have the big question all the time, can tornadoes become absorbed into each other? Not necessarily. I mean, they can weaken and one can kind of reabsorb it. And I think that's what happened in this case. No, they don't just absorb and become a super tornado or anything like that. But most of the time, since they have wind directions that are rotating the same direction, the region between one part of a tornado and the other part is adjacent, almost like magnets. And they call what's called the Fujiwara effect. And I'm not even going to start talking about that one, but that's when they don't really absorb in each other, but they want to circulate around each other like that because they're like two opposing magnets in a way. So I think that's what actually happened with this tornado when it occurred, but I had to go back and actually catch this velocity imagery. And I was just breathtaking to see two couplets like that. You can't get really any worse than that because they were both large, violent tornadoes. It wasn't one weak and one strong. They were both large and violent. So tornadoes come in all shapes and sizes that could be named just about anything you would want to call it. You see this tornado types chart, you got wire, rope, a needle, a V-shaped. You can call kind of weird things. However, we're going to focus on the most common type along the northern Gulf Coast. We have the multi-vortex tornado. That is many sub-vortices within one parent rotation. These vortices can add over 100 miles per hour to the ground relative wind in a tornado circulation. So that's stronger little tornadoes and a big parent tornado. So this actually happens. And what that kind of looks like is something like this. You get one big parent rotation you see there with the big kind of the transparent condensation. We see those little tiny funnels all within it. Those can be way stronger within it. And sometimes we see some really interesting debris or signatures on doing tornado surveys. You can actually see, that's why sometimes people say one house got hit and the other didn't. But sometimes that there was a multi-vortex tornado and there was a little rotation that hit one house. That was probably the width of the house. You just can't, you don't know where it's going to go because they're just developing and circulating in one parent rotation. So what does a multi-vortex look like? I will tell you this, that multi-vortex tornadoes are a very, very common type of tornado down here. They're very messy looking. You see there's all kind of wild different wind directions and curling of the winds, but mostly what you're seeing here is a multi-vortex. And I know it looked a little bit better before, but it's still looking kind of chunky here. But this is still a tornado. There you go. You can actually see a really good couple of vortices there. And you see that they form and then they dissipate. They don't last that long, but where they form and they happen to strike your house, if you get directly underneath that circulation, it can flatten your house. You can see here, that's extremely good footage of it there. You see all these little vortices rotating around that parent axis. So it's actually extremely interesting how these multi-vortex tornadoes occur. And that, that's amazing footage actually. I don't think I've looked past this much into it, but that is absolutely fascinating. So a wedge tornado, if you've ever heard of what is a wedge tornado, it's typically referred to a tornado that is wider at the ground than the distance from the ground and the cloud base. So wider at the ground than the distance between the ground and the cloud base. So it's just wider at its width, basically. These can actually occur a lot down here. This was an example of the Acres tornado I showed you before, that classic supercell image. That was an EF3, not EF1, but that was a large wedge tornado that came across. What do they look like? Well, here's footage of one. I'm not 100% sure what this was. I don't think this was in Louisiana, but this is a wedge tornado. It's a very low cloud base, very wide tornado. Actually, I want to say this looks like actually, I know this one. This is the Phil Campbell EF5 on April 27, 2011. I want to strongly say that's got to be that the tornado there, because I remember that day very well. That was an EF5, and that was a wedge tornado, a deadly tornado as well. What types of waterspouts? We have non-tornadic or fair weather waterspouts, believe it or not. Yes, we can actually just have fair weather or non-tornadic waterspouts. These are waterspouts that don't have a parent mesocyclone to them. They look like this. This is a view from the Hilton at New Orleans Riverside of a weak waterspout over Lake Pontchartrain. Something like this, they can be dangerous. You don't want to drive your boat through them. And I know there's been YouTube videos of people who have done it. And fortunately, it was a weak waterspout like this, but they're mostly weak. They're talking about winds of maybe 40 to 80 miles per hour. However, the stronger tornadic rooted to a mesocyclone type waterspouts, those are the big ones. They can have way stronger winds in them. They can cause damage. If you're in a boat, it can capsize your boat and can be deadly as well. So this was one of large waterspout and sister smaller waterspout over Lake Pontchartrain. That was one on February 23rd. That was mesocyclone induced. There was actually a couplet you can see on radar, and then this was occurring at that time. That's one you do not want to get inside. That's when you stay. Of course, there are smaller ones outside of it, some sister satellite tornadoes or satellite waterspouts, but the main waterspout there is what we call a tornadic or a rooted to a mesocyclone waterspout. Now, the threat to consider with that waterspouts that can come on shore is a tornado. That happens a lot because you see the densely populated areas across Lake Pontchartrain and across coastal Mississippi. Now, these occur more in the late spring to summer months, and these can be very challenging to provide good enough lead time. This is an example here of the Michoud, New Orleans waterspout that occurred and Orleans Parish on July 18, 2019. I like to show this one because it was extremely photogenic. However, I'm going to go to radar here, and I'm going to basically see if you can spot where that waterspout was. Here, I'll go back. I'll start again. You got the reds and greens. By the way, the radar is to your kind of up top of your screen. So you got the greens towards and some of those reds away. So there's some cyclonic rotation, but do you see it? Do you ever see a couplet? Did you see it? I didn't either. Very small area was there though. There was a very small one about right there. That was where the tornado was spotted. I barely saw that. Very hard to identify them. When they come on shore, they can cause damage and sometimes have very little lead time, unfortunately. But with the stronger mesocyclonic ones, this is one that had a couplet to it. This was an example on February 23rd, 2016. This is the Madisonville EF0. This was a larger waterspout that came on shore with around, I want to say 80 to 90 mile per hour winds as it came on. As you can see it, there's the couplet, keeps going. In fact, hey, right there, I like that one a lot there because you actually see two small couplets. That's two waterspouts at one point. And then that looks pretty good. And we did actually end up issuing a tornado warning just for that small slither, including Madisonville, where it made landfall. So they can come on shore. Sometimes they're a little bit clearer to see and easier to see, but sometimes they're not. The main story here is that if we are lucky enough to warn one of these, you got to take them seriously. And spotting these are extremely difficult because they're rain wrapped and usually they're very hard to see. So you got to use an extreme amount of caution with these. And also when they come on shore, they have a tendency to dissipate relatively quick. Once they come on shore, they dissipate. They don't just keep tracking inland. That almost never happens, although it has happened before, but it doesn't happen often. This tornado only ran into a small boat launch here. You see with these pictures, rated an EF0. Okay, the winds were actually at 65 miles per hour with this one. So it caused damage to a boat launch, but it did not go any further than that. So your report matters. While we're talking about all this, your report can help provide lead time to protect those in the path of the storm. This is an example of having that report was May 9th, 2012, when a train spotter reported a waterspout just barely, it was just to the north and northwest of Grand Isle there. That gave enough people lead time to take action. So you see the polygon there, you see a little bit of rotation there, some greens and reds there, but that was a big waterspout that came on shore. So with that, actually, I thought I had a video with it, but I don't. So with that, I think I actually have another video on that one coming up here. But yes, this was a one we actually had to issue a tornado warning for, due to the fact that we had that confirmation of a large waterspout heading towards the southeast, and it crossed over Grand Isle and caused damage. So I'm going to jump straight into the true-false questions. This is the wrap-up of the presentation, and these are going to be rapid-fire true-false questions. So you got to be ready for this one. True or false? These are myths. Again, these are tornado myths. Remember this. So true or false? Living on a hill can protect you from a tornado. I've heard that my whole life. Is it true? Let's see if this works here. I'm going to launch it. All right, it's open, ready to go. Living on a hill can protect you from a tornado. I'm going to tell you something. I've heard both my whole life, but there is truth to it. Oh, wow. I like it. I'm going to go ahead and close it. All right. Look at that confidence. Wow. Great job. I like that a lot. All right, we're going to hide that and go back. What's the answer? False. Great job. Tornadoes can travel up and down hillsides and are just as violent and dangerous. And for that video, just recently, Meadowbrook, Alabama, that happened on March 25th, 2021. So this is just about a month ago. This person's driving out Highway 280. I'm from Central Alabama. I know exactly where he's at here, but watch that tornado go up that hill. It's going up the hill. It's not stopping. It's definitely not slowing down. It's not weakening either. So it's climbing the hill like it's not even there. So it has happened. We've had stories of it happening, and it can happen too. And there's a little also too. You see all that wind, rain, and clouds at the backside of it. That's the rear flank downdraft following the backside of it. There's very high winds going on down that road. But that was it. The tornado did become a little bit disorganized when it hit the top of the hill, but still, it continued up the hill like it wasn't even there. So that is false. Poll question number 2, true, false. Opening the windows in your house before tornado will reduce the damage by balancing the pressure inside and outside the structure. I think that should be just inside the structure, or it should be balancing the pressure between the inside and the outside, that is. So this is this one I've also heard ever since I was a kid. Opening the windows. Should you open your windows before tornado? Will it reduce damage? Ah, very good. Okay. So this one's got pretty good confidence to it. All right. Well, okay, we're getting more. If I keep seeing changes, I want to be a little hesitant there. We'll go ahead and close it and share it. Ah, very good. Mostly false, but some true. That's very interesting. Okay, I like that. All right, let's see if we go back to it. The answer is false. Opening the windows is absolutely useless these days. It was an old thing to do. I remember, I'm not that old actually, and I remember when my parents did it. So it's a myth that's lived on a very long time. It could be a waste of time. In fact, sometimes some people could say that you could increase the risk to damage to your home because you're introducing wind into your home, which if enough wind gets into your home, it can then get up to the roof and faster remove the roof off your roof. So you want to actually keep your doors and windows shut at all times. That would be the best thing. Remember, most of the time we get roofs that are removed and wall failure collapsing, from what I've learned, is actually the garage door bowing inside. That's because the garage door is one of the weaker parts of the house, weaker than a door, but it can bow in. And when it bows in, all that air rushes into the house and it lifts off the roof, and then you get total destruction. So if you have windows open, you're just introducing the chance for more wind to come into the house, lift up the roof, and cause devastation. So no, do not do that. It has nothing to do with pressure, air pressure, anything like that. Just definitely get to your safe place. Don't even worry about that. True, false. Got another one. It is not safe to take shelter under a highway overpass. Not safe. So we're going to launch that one. Oh, wow, there we go. It is not safe. Now, I've heard this one. All these, again, these are very good common myths that have happened. And these are myths of people have done this in the past. That's why I'm bringing these up, to kind of take out the myths here. So I want you to think of it. I mean, you got a highway overpass and you're driving along. I mean, what do? You stay in your car? Do you get in a ditch, or do you feel safer under a highway overpass? So we're going to go ahead and close that one, share it. Oh man, I love it when it's a little bit mixed. I mean, there's a bias to it, so it looks like true is a pretty good overall estimate. That's great. That's fantastic. A little bit false. Whoops, I need to go back to the screen. There we go. And back here, the answer is true. If you're in a vehicle and a tornado is approaching, of course, remember this: you should pull you pull your vehicle to the side of the road immediately. Get out, and I know you don't want to do this, but lay flat in a nearby ditch, covering your neck and head. I know you don't want to do it. I know one wants to get out in it, but if you stay in your car, it can tumble. If you get up in the overpass, you just don't want to do it. So I'm going to show this now. I don't have sound to it, so let me explain. I have sound to it, but I'm not sure if it'll work. But I'm going to explain to you. This was a clip from Weather Extreme Tornado of someone who was actually interviewed, and I'll tell him what he's saying. Here, let me move ahead to it. This was actually a true story during, I want to say, I'm not sure if it was the Moore, Oklahoma tornado, but it was one of them. This person here, he didn't know what to do. There was a tornado approaching. He got up. He thought he did the right thing. He went up underneath the girders, up underneath the overpass, and he sat up there. He's actually showing there. You see those indentions. That's the body prints of where they were staying there. So mud was being splashed upon them. He was holding on to dear life to that metal part there. And he had a lady and if I recall correctly, a lady and her daughter was behind them. And as the tornado in this very okay looking animation shows, as it comes across, the tornado went directly on top of them, and they held on to dear life, and they were being completely just splattered with mud. And in the story, he explains that he heard the lady behind him, and then the next second she was gone. She actually got sucked out from the tornado and died. So don't do it. I know it feels safe to have something heavy and foundation like that, but you're going high up into the air. You're exposing yourself, and sometimes the winds funnel higher in an overpass like that because it's such a small corridor. Just don't do it. If you see the tornado approaching, if you think you could turn around and go, that's fine. But most of the time, if you know you can't outrun it, get out of your car. Your car can be a flying missile. And if you're inside of it, the tornado tumbles. The tornado will tumble your car, and you will be killed. And I hate to say this, but a lot of fatalities have been in cars because of people who stay in their car. They don't want to get out. If you get low in your stomach in a ditch and you cover your neck and head, it'll protect you from the debris. The debris will be flying around you, but if you don't have anything between you and the ground, the wind can't come up underneath you and pick you up. That's why they say to do it. Poll question number 4. Tornadoes do not hit big cities. I've heard that one a lot too. Let's see here. I'm going to launch that one. True or false? Tornadoes do not hit big cities. All right. Very, very good. Very good confidence. All right. Gosh. I thought I'd throw a pretty easy one out. I guess this was an easy one. There you go. Yeah. Pretty much, yeah, they without a doubt can hit and have hit big cities. So don't think that you're protected at all. Yeah, the answer to that is false. They have hit big cities, several cities in history, including Dallas, Miami, Minneapolis, New Orleans, because I just showed the New Orleans East tornado. Atlanta, Salt Lake City, all have had one. This was the famous May 12, 1997 Miami tornado. Waterspout that came ashore as an F1. Windows and outer walls blown out the Bank One building from downtown Fort Worth, Texas in 2000. And of course, the perfect example I just brought up, February 7, 2017, New Orleans East tornado. So yes, they can happen in big cities. I know they've been talking about they haven't had a major tornado hit Dallas or anything like that. And they've been trying to stress, just because it hasn't happened, just because they haven't had a major tornado go through Dallas doesn't mean it's not going to happen. So everywhere, everybody's susceptible to having a major tornado come through. This one, yeah, this is a good question here. A tornado is more likely to hit a mobile home park. I've heard that too so much about, oh, it's another mobile home park. It got hit again. Let's see, I'm going to start that one. Are they more likely to hit mobile home parks? Almost like, think of it as like our mobile home parks tornado magnets. And we've heard that our mobile home parks tornado magnets. Well, you know, think about that. Okay, very good. See some very good results coming in. All right, I think that'll be good. We'll just go ahead and do that one. All right, and share it. Very good. Majority false, some true. Okay, very good. We'll go back. Whoops, want to make sure we're on the screen. There we go. The answer is false. Tornadoes are not likely to not more likely to hit a mobile home park. Chances of them be doing more damage and destruction to mobile homes are greater just because they're mobile homes and sometimes they're not tied down. In fact, Louisiana is ranked, this is an interesting statistic that I remember here. It's ranked number 3 out of 50 states. That's Louisiana is ranked number 3 out of 50 states with the most manufactured home. And current statistic here is 37,000 as of April 2020. The damage seen in mobile home parks are significantly worse than what could occur in a neighborhood in framed homes. Even the weakest of tornadoes can flip mobile homes. I have seen damage. This is actually a damage from Watson, Louisiana EF3 from February 7th. I have been on surveys where I've seen just the smallest tornado ever, and the home is just may have some shingles gone or a tree down, but the mobile home is just completely destroyed and flattened. You think to yourself that there must have been an EF4 that hit the mobile home, but the house was fine. They're a weaker structure. They don't have solid foundation walls, and sometimes they're not even tied down. I'm sure this one, this example here, I'm sure it was not tied down. And that's why if you're in a mobile home, you've got to get out. You cannot be in a mobile home when there's a tornado. Now, available products, there are many products online that can help you right at your fingertips. They're going to provide you with more detailed threat-specific weather information. One of those is showed before, the Storm Prediction Center, where you can check out convective outlooks. They give out the slight marginal, slight, enhanced, moderate, high risk. This is fantastic if you want to kind of prepare. If you think you're going to be storm chasing, you say, okay, we got a moderate risk on day 3. So 3 days from now, I need to be ready for it. I need to watch and monitor for trends. So you can see that they change through days. The mesoanalysis page, if I showed you some information that you like with these parameters, these atmospheric parameters, it's like those 2D images I was showing the graphics from, this Storm Prediction Center actually has the mesoanalysis page. This is a tool used for forecasters, but if you know what you're looking for, it can be a good tool for forecasting as well. It's updated frequently to provide an idea of the environmental conditions hours before severe weather strikes. So you'll have an idea of the thermodynamics. You'll have an idea of the instability, like I just said, and the vertical wind shear before the severe weather even forms. So do your own analysis. If you want to learn more and do your own analysis, and that can help you better understand what the severe weather potential is. Also, you have the Weather Prediction Center, WPC at ncep.noaa.gov, that does a similar convective outlook type format, similar to the SPC, that uses a marginal, slight, moderate, and high risk category. Very good and very accurate with depicting risk for flash flooding. Visit our website, National Weather Service, nws.noaa.gov/New Orleans or /LIX. You can get the latest information there too. Now, we no longer, if you happen to remember, if you happen to know, we used to do a legacy text product called the Hazardous Weather Outlook. We have quit doing that. We are now doing something a little bit, hopefully better, to attract more people and a little bit more clear way of understanding threat messages, using what's called the Enhanced Hazardous Weather Outlook, which is actually graphically produced instead of it being a text product. So you can actually access this by our webpage. If you go to our webpage and go to the very bottom, you'll see this colored graph I'm highlighting there. And what it looks like is to the right, you have a graph across the entire area, our area of Southeast Louisiana and Southern Mississippi, that shows you threat-specific severe thunderstorm risk, lightning risk, flooding risk, fog risk. I'm just reading down a few of these. Frost and freeze when we get it just a few times a year. All these different risks done from a scale from none to limited to elevated to significant to extreme. So we thought that's a little bit better at graphically portraying what the risk for any type of hazardous weather would be. So check that out sometime. It's a graph that's produced in-house. We have control of designing what it looks like, where the threats look the highest. So give it a look sometime as well. And then for technical discussions, we write what are called AFDs, or area forecast discussions. These go out with every main forecast package and update throughout the day. So we do 2 main forecast packages at 4 a.m. and 4 p.m. The forecast is completely updated all the way through day 7. Frequently during the day, we may do a short-term update. We may do a morning update or an evening update or something like that. If the weather is changing different from our forecast, we want to make sure our forecast lines up correctly and reflects the latest model trends. What we'll do is we will adjust the forecast, and then we'll write a discussion explaining why we adjusted it and what areas to focus on. So they can range from being very brief to sometimes very in-depth. I'm very guilty of writing the in-depth ones. And they can give you a little bit of a heads up. Sometimes you can get a little bit of a gauge of forecaster confidence. You can actually, like for example, here in the bottom, maybe we're not messaging this. Maybe there's no outlook from the Storm Prediction Center, but I just highlighted here, someone wrote severe thunderstorm potential appears low during this period, but a few stronger storms with gusty winds can't be ruled out. Well, you're not going to get that in a SPC outlook possibly. So, or maybe not even the enhanced weather outlook, but you can, again, understand why the weather is occurring and justification to why we're changing or leaning towards one or the other. So give that a look sometime. That's on the bottom of our webpage. You go to our text products, you'll search down and find area forecast discussion. So reporting severe weather, of course, I showed you with the basic course. It's at the very bottom there. You'll see that SkyWarn icon. It'll take you to this page. I personally think this is one of the best ways. You can call it in, you can tweet it, you can put it on Facebook, but here it's completely anonymous. You go on the Facebook, you go into the Google form, you put in your information, who you are. If you're a train spotter, please tell us that you're a train spotter, because that increases confidence that what you're looking at is likely you're trained and know what you're looking at. And we all get this. This is instantaneously emailed directly to all forecasters. So if you're reporting a 1/4 inch hail, or say that you're reporting 1 inch hail, and you need to submit it, go on this webpage, click that button, enter your information, hit submit. You're done. You did your job as a storm spotter. You helped us by getting ground truth. So that's one way you can do it as well. One other tool that I didn't talk much about from the basic course, but is available here, is the MPing. MPing is an app, actually, and it stands for Meteorological Phenomena Identification Near the Ground. It was designed by the NSSL and SIMS, which is 2 research areas up across way far from here, who did one of SIMS, of course. They did a lot of research too about trying to find a way to get a collective observation record of what actually is occurring at the ground. So again, radar doesn't see what's going on the ground, but if you get a bunch of people with their iPhones reporting what they're seeing, you get something like this. And this was during a winter storm. You can actually see where it's snowing and sleeting or raining, or there's a mix. Because remember, the radar is not going to always scan. Exactly, it scans higher up, and it doesn't really tell. If you remember from the correlation coefficient talk, I was saying with the rain-snow mix, you don't really know if that's occurring at the ground because we're scanning aloft. But with this here, you got that ability. So if you have a smartphone or any type of smartphone, find MPing and download it. It's completely free. You can download it. Now, I can't basically talk much about this one or promote it much, but if you happen to have RadarScope, which is an app that's available through the App Store, you can put in these MPing reports there. Again, I can't promote it, but if you happen to have that app, you can submit MPing reports there as well. But if you don't want RadarScope, because RadarScope does cost, I don't know how much it costs, but it's a great tool to do radar analysis on your phone. I use it myself even. And you can submit these reports. If you don't have that, you don't want to pay for it, you can just download the free MPing app. You can, it just brings up something like this. It uses your GPS location. You select report type. You say you saw wind damage. You saw a 1-inch tree, limbs broken, shingles blown off. You hit submit, and we get it instantaneously, just like your anonymous report that you gave us through our webpage. These pop up. These are actually overlaid on our radar imagery in-house. If we're seeing a storm and you just submitted that there's wind damage and we're not sure we should pull the warning yet, we're on the line, you just reported wind damage. Oh gosh, okay, well, the winds are starting to transfer down. We need to issue a warning quick. Although it'd be reactive, but hey, at least we got something out for people downstream. Follow us on social media, website. We got our website here, Twitter, Facebook, and we're becoming more active on YouTube also. So follow us there as well. And of course, remember why reporting severe weather is so important. It starts with what you see. When you're out there seeing something and you think you may be seeing a funnel cloud, or you think you may be seeing a tornado, and you call it in, that gives confidence to us that we know what we're doing, which in turn helps protect lives and property, which is the mission of the National Weather Service. So as a reminder, always report. I should probably take the left side off here. I say hail, dime size, or large, or severe criteria is 1 inch. If you see any hail reported, if you see any strong damaging winds reported, if it's like 25-mile-per-hour winds, there's no reason to report that. Tornadoes or funnels, widespread flooding. Yes, we actually need flooding reports just as important too. That helps us understand that we sometimes are on the fence about a flash flood warning, but if we're getting reports of flooding, we need to hurry up and issue it now so people will know, anyone who gets out to go driving, they should be careful. Give your location and the time. Remember, give the time when severe weather occurred, not the current time when you're given that. Express who, what, when, where, who you are. Say you're a trained storm spotter, what you witnessed, when it occurred, and where the event occurred. Of course, we have some people in amateur radio. That's still a program that exists. Of course, with COVID, we had to hit protocols where we couldn't have some ham radio operators come into the office to help with that, but we still do that. I don't, truthfully, myself, I don't have a ham radio license myself. It's kind of technology's kind of evolved a little bit more into now everyone has cell phones, and reporting severe weather is a lot faster and easier through your cell phone. So, but these still do exist. Here's some information in case you're interested. And if you're interested in becoming a cooperative observer program, this is something I added new. The co-op program is a system of 11,000 volunteers across the United States. You can actually become trained, and you are given equipment and you're getting free maintenance, and only thing you do is provide daily data. That's it. If you're really passionate and like about giving observations, you like to give daily high, lows, and precipitation. If you're really interested in this, contact our observing program leader, Sean O'Neill, at sean.o'neill@noaa.gov. I'll give it here a few seconds if you want to jot that down. If you're interested, he will gladly get you set up. He's fantastic. We call him an OPL, a fantastic, and he's a meteorologist and forecaster as well. Fantastic guy. He will definitely get you set up on that. And if you just want to report rain, go to cocoros.org and you become a CocoRoS observer. You can actually help report rain in your location. So you can go to the CocoRoS app as well. If you're interested, email me or email Sean, and Sean probably knows more about it than I do. He's our observing programs leader, so he'll know a lot more. If you're looking for additional training, if I cover something like, man, I didn't quite understand what he meant by CDR. Maybe I should go back and do some training. Go to MetEd. It's completely free to register. Just register, and you can find any class you want. You can retake spotter classes. Yes, they actually have basic and advanced courses there. They have comprehension and different difficulty levels will vary. And of course, a new thing that's coming out through National Weather Service is now the Jetstream. This one, I actually got a lot of images and information from Jetstream. It's a fantastic tool. It's a lot used with education, usually for those who are like teachers who are teaching meteorology, school classes teaching meteorology. It's a fantastic way to maybe create a curriculum if there's any teachers that are on right now. Please go to that. Jetstream will have all the information that you need. It's weather.gov/Jetstream. Just search a topic. If you didn't understand parcel theory or something I went through, which is like, what's a SKU-T again? They have a huge, great overview of what a SKU-T is there. So give that a try. Congratulations, you made it. We all finished there. There's our address to the top right, phone number. Of course, that's our direct phone number. So if you have those two phone numbers there and use extension 4, you'll get me or anybody else working 24/7. So if you're a storm spotter and you got to call in, I see a tornado or funnel cloud, you got our number right there. You got our website on how to submit reports. You got MPing, you can do that. You can shoot us a private message on Facebook or comment on Facebook. You can shoot us a tweet on Twitter. All these are different avenues for you to give us any type of important information to help protect life and property. There's my work email there. Feel free, any comments, anything like that. You'll get a certificate in about 1 hour after this presentation's over, and it'll be your storm spotter certificate. What you want to do there is you need to fill out the form. This is going to be for our database, so that we're trying to keep track of all our storm spotters and how many we have and from where. And there's going to be some cool detailed questions like, do you have a weather station and things like that. There's some information that's optional. You don't have to give your phone number or things like that, but that would be extremely helpful. And again, just fill out that form and you'll get your certificate directly right after. It'll come from my email address. So you'll see, if you don't have to jot down my email address, you'll get mine from the certificate email and the receipt of the information that you sent. So congratulations, we made it this far. I'm going to check some of the questions here. I've been seeing some questions here. Let me bounce out of here. Let's see, do you see the MPing report, or should we also call in the report? I'll say that if you're more comfortable, call it in, please call it in. MPEG's more for convenience. It's just you pick up your phone, you hit it, and you're done. If that's more convenient to you and you really don't feel like calling or you can't call, then don't do it. I would say honestly, if you could like maybe choose between the two, probably I would say calling is more important. Probably because you can maybe relay it to us a little bit more clearly. Like, hey, I'm an advanced storm spotter. I've been in your advanced classes. I know for sure I'm safe. You can maybe even portray confidence with that. We can talk to you for a brief moment. So I would say maybe if you have the ability to call, please call. That would be extremely important. So yeah, that's great. So got a lot of questions here. Okay, Mira, got and got a lot of cool, great comments here. I'm enjoying Doc Morris. I like you a lot. Doc Morris, you're hilarious. Yeah, I've got some. I'm trying to see if I'm missing any. Recording be available. Yes, as of right there, the session is being recorded. I will have this uploaded. My goal, I don't know if we have the ability to put this on our website just because it is so much. I don't know if we have the space to do that because this is a 2-hour, almost 3-hour talk. So definitely, I don't know if we have the space to do it. I will try my hardest to try and get these. I got a basic and advanced I'm going to put on our website. If we have the space to do it, just look for weather.gov/licks or New Orleans/SkyWarn. If you check that, just check back in maybe another week or two if you want to go back through this again and see if there's going to be maybe a link for a basic and advanced. We've had a lot of questions about it. I think this specific course will be one of the advanced ones that go on there, and if we have a basic one as well. So yeah, if anyone's got a question, this is your time to chat with a meteorologist from the National Weather Service. So this is your time to get out any question. I mean, I'll just keep it going for like another minute or two. If you have anything, definitely now is the time. But we appreciate everyone joining. This was fantastic. Hopefully I didn't miss anyone's question. If I did, please re-ask it. Yeah, okay, I don't think I missed anything. All right, I don't think I missed anything. We'll end there. Thanks so much for joining. Like I say, you should get your certificate. Oh, got a question. If we want to pick up an anemometer, is there one you suggest? I get the question a lot. And I think I'm gonna add that to some future spotter talks. People always ask about home weather stations. And I think that's whether I can't, of course, I can't say like, one's better than another. I don't want it to be a conflict of interest or anything like that. But I can tell you, just on the down low, what I personally like, I have a Davis weather station, a Vantage Pro 2. They could be expensive. It really just depends. If you want one where you don't want to worry about it and you want all of it in all in one package, I would say that the weather flow or I want to say it's the weather flow stations by Tempest Weather. I got my phone right next to me as I talk. Let me look that up real quick. It's the weather flow weather station. Yeah, it's weather flow wind station. That's it. Yeah, I just brought it up. It's the one that I personally am thinking about buying myself because that's actually one that you can get your information on your phone. Like your weather station, what it's observing, instead of it going to a display, can actually go to your phone. And I think that's really cool. And you can try that out. Their price is at around $200 to $300 range. Again, it just depends on how much you're willing to pay. But I have a Davis Vantage Pro 2. The only disadvantage with those is, and it's wireless, but the only disadvantage with those is you have to buy a data logger to get the information online. And I don't even have a data logger yet. I just have a display that I look at if I want to know the temperature, the wind speed, and how much rain's falling and things like that. Okay, Todd, I will definitely check. Thanks for bringing that up. I'll definitely check. In fact, I got a sticky note right here. Whoops. And I will definitely check that when we get done here. If not tonight, then tomorrow for sure. I'm writing your name down. I will check about a basic. Thank you so much for reminding me. Can you talk about the wake low? Oh no. Actually, hang on a second. Let me go back to the let me go back to the wind question there. So Davis is a good one. Oh gosh, there's just so many of them. If you go to Amazon, just shop. That's one option. I know Lowe's and Home Depot have weather stations as well. I would say probably the best winometer that I've ever dealt with is, of course, the Davis Vantage Pro 2, but those are expensive. Try out WeatherFlow. Look at that. That really has some of the best technology today, and is I call it a relatively fair price. So give that a try. Can you talk about the wake low pressure system and that formed ahead of the squall line that contributed to the collapsing? Yeah, that was a hefty event. I was working the midnight shift during that one, so I remember it leading up to it. A wake low, that is a very complicated a very complicated process in the atmosphere that occurred that day. That was in the response to a strengthening MCS, or what we call a mesoscale convective system, or it's a complex of thunderstorms that has a lot of damaging high winds. Basically what happened was it shot across I-10-12 towards Baton Rouge, and it took a right turn and went straight south. And when it did that, it created an MCV and a mesoscale convective vortex, and it shot this MCS fast south. And we actually tapped into a low-level jet. All that transferred down and just blew out winds over 100 plus miles per hour estimated. We got some, believe it or not, weather flow sites. Because by the way, if you get a weather flow, we can track your weather station as well. We got some weather flow sites, one which I don't think is a weather flow site. One's actually a buoy on Grand Isle, gusted at 75 miles per hour. So when that one gusted at 75 miles per hour, we knew this was a serious deal. So when that came across, that was the squall line that came across. Now what happens is when you got so much lift out ahead of a squall line, I mean, that's what a squall line is. It's that cool, stable air pushing that warm air up above it. And you got a lot of rising motion, and you've got a lot of air going up onto the top of the troposphere. Eventually it's got to come back down, and when it comes back down, it's sinking, and when it sinks, it cools, compresses, and it sinks, it cools and sinks down to the surface like a high pressure center. We call that a meso high. So yes, ahead of a squall line, you got a squall line, and then you got a meso high. Now it's incredible. It's actually air that's pouring down like you're pouring a cup of water down to a table. So it's pouring down, and when it pours down, that air goes backwards behind that meso high. So it actually, the squall line, of course, for that event the winds were heading from the north to the south. But when the meso high passes, the winds were going from the south to the north. And you get what's called a wake low, which are pressure perturbation differential. Yeah, that was a mouthful, I know. But what you get there is a wake low. So you get rapid rising in response to that rapid sinking, which almost acts like a large scale gravity wave. So you get these high winds on the backside of an MCS that just blow through, and sometimes they're very hard to predict. They're extremely difficult. They even forecast those, and we did not forecast this. Models don't pick up on this. It's a large scale response, basically, in a way of saying that. We saw the cold pool possible was there because that's a response from the squall line, but we didn't expect the response from that. And if you want to get into technicalities, we can. We just did an after action review yesterday, going over what went wrong, what went right, going to the in-depth science part, one that I even did a presentation about. And we actually ended up finding out that prior to the event, prior to the MCS approaching here, we had a very strong substance aversion in the lowest troposphere. And it acted like a trap. So when when the air went back down as a meso high and it wanted to go back up, it couldn't because it hit the substance aversion. So it created a wave pattern. So and then of course you're going to get the high winds from that. So not a typical event, but they can happen, and they're not well forecasted, I hate to say. Usually we go with a reactive high wind warning, which we don't issue high wind warnings that often for just pressure gradient events like a cold front. Usually those are wind advisories. But for this one, I can't remember if we did issue a high wind warning. I think we did. Some offices, and sometimes there's a differentiated philosophy with this. Sometimes they'll issue even a severe thunderstorm warning when there's not really technically a severe thunderstorm going on. It's actually just due to high winds. There's different modes of thought with that. You can go either way. Technically, you're supposed to do a high wind warning, but you can go with the severe thunderstorm warning as well if you want the message to get out. Let's see here. Let's see. There's more. Sorry. Yeah, the recent. Yeah, I don't know if it was a write-up, but yeah, I'm talking about the one that went across. It did go across Baton Rouge pretty heavily there, and then it went across Baton Rouge and then made that south to southeast clock towards the southeast coastline of Louisiana, and then went across the coastal areas. that was extremely intensive. And I will say that the models did a fantastic job on it, because I was the one forecasting the night before. We tried with a heads up. We said that we were looking at the cam guidance, and we were definitely saying that it's going to be an MCS that's going to take a right turn, which it can do that, especially because the boundary draped across Plaquemines Parish. You're from I-1012, just south of I-1012, and then draped to the southeast, and it just rode like a train on a track. It rode that and went right down. And usually that's an amplification when you get that inflow. You're increasing the updraft inflow into it, which can also increase the cold pull behind it, which makes you have stronger winds in the backside. Yeah. Yeah. So on the roof, okay, I got you, Doc Morris. I'm reading right now. It says on those roofs. Yeah, I'm on roof. Okay, he says I'm on those roofs daily. Shingle damage seems more damage on the downwind sides of roofs than on the from side, but I don't know about that. I mean, yeah, you say you do roofs, you may know more about it. I've installed shingles before. It's weird how it works like that. From what I remember, shingles really kind of come off in like chunks and pieces, but I don't know if there's any like actual correlation to the wind direction. Okay, well, all right. Roofing sales and inspector. Yeah, I did it just to do it once, and I'm sure I didn't do that good of a job. But it'd be very interesting to know. I don't know if there's any like actual correlation to a specific side. I would think that the side where the wind blows towards, so I guess that would be upwind. I would think that if the roof is angled down and the upwind hits it, doesn't the wind try and get up underneath the shingle and pull them up a little bit? Eventually, they'll tear and fly off. I would think the problem is that the air is trying to get up underneath the shingle where it lays on top of the one below it. That would usually be the problem, but I don't know why they would rip off on the downwind. That would seem very interesting. I'm not 100% sure, but shingles happens. Shingles is one of the first things you get from high winds with damage to a house. Is usually you lose some shingles along with trees too that fall outside on the property. But okay, I think I've covered pretty much everything there. I would say that's pretty much it. I'm sorry I went 3 hours on this. I'm very involved. I'm very passionate with what I do, and I want you all to be as well covered about this topic as possible. That's why I said multiple times, please do some more training. Or if you want more training, please do more training if I didn't catch anything, because I can't do this for 8 hours. If I could, I probably would, but I try to condense this down as much as possible. So hopefully you got some good information out of this, and this will help you out a lot. Again, expect the certificate coming along soon. If you don't get it, if there's an error, please do me a favor and shoot me an email and say, hey, the form didn't work, or something didn't happen right. And this is a new form. This is the first year we're trying this automatic form. And we've had a couple little hiccups here and there. So if there's a hiccup, don't feel bad. Just shoot me an email and say, hey, Kevin, just a heads up, I didn't get my certificate, or it didn't come through, or it's wrong and I need it to be corrected. I can personally change it for you. All right. Yeah, thank you. That's great. I appreciate it. I'm glad everyone appreciated it. Thanks for joining again. You got my email if you ever need it. So y'all take care, and thanks for joining.